I'm Kat. I flew in from Michigan last night. I wrote probably about half a simple CV with my partners. We've been around for about 2 years-ish. I think the first commit was about 2 years ago. So just getting started, like I've already said, install a VirtualBox, get the image going. You may want to tweak the VirtualBox settings so you get a little bit better experience. The reason we're doing this way versus having you install everything is that, and I'll get into this, we have about 10 core dependencies and 15 optional libraries. So getting everyone up and running and installed with like the full list of everything takes a while, and this is the quickest way to get people going. Once we're done with everything, if you guys want to go home and give this a shot on your own and put it on your host operating or your native operating system, please do. If you have any issues, you can basically get help or see the basically install list in GitHub, which at the Simple CV repo. We hopefully will kind of fix this experience later on in the year, and hopefully have, right now we have super packs, they're a little outdated, but they get you most of the dependencies. We're gonna clean that up probably after a release this summer, and it'll be a lot cleaner. So about the format of the tutorial, I really, really want you guys writing code and seeing how things work. So I'll kind of lead. I have a copy of the notebook here, and you guys can follow along. And I want you to feel free to interrupt and be like, hey, what's going on? This is crazy stuff. I don't want any of this to appear hard. Like, if you don't get something, please feel free to stop me, because if you don't get it, probably a bunch of other people don't. And if you have any issues that are kind of related to VirtualBox, if you raise your hand, I'll see if I can get somebody to assist you. I can't totally stop everything, but hopefully we can get you some help. So what is in Simple CV? Like, you hear about this library, like what's going on, what's in there? So we're not exclusively OpenCV. OpenCV is a primarily C++ library for doing computer vision work. They are super awesome in the sense that they give us really rough Python bindings that we can play with. It's not the most user-friendly thing in the world. So what we've done is we've taken those raw bindings, we wrap them up, we clean them up. We present an interface that is more of how you want to think about problems and how you want to use it. And we add in a lot of other tools that would make it easy to interface with, say, NumPy or SciPy or scikit-learn or a lot of the other tools in there. So that means you get stuff like that isn't native to OpenCV. So you get OCR support, you get barcode reading, you get all these sorts of tools that aren't built into OpenCV. And generally, our purpose is different. We do lots of easy sort of Python problems for computer vision pertaining to, say, manufacturing. C++ and OpenCV is really great for like embedded stuff that needs to be the latest and greatest and super fast. We don't need to do latest, greatest, super fast. We need to solve practical problems every day. Okay, so the core dependencies. What's in Simple CV starts out with OpenCV Python bindings. We then have NumPy, SciPy, scikit-learn, and Orange. Right now we primarily use Orange for machine learning. We'll probably switch over a little bit to scikit-learn. Pygame, which is what we use for rendering and doing some of the display stuff. We use PIL, which is the Python imaging library, to help us marshal some of the data in and out mainly. And we also use IPython, which is essentially a Python notebook, interactive REPL. There's also a lot of optional dependencies that we roll in. We use either zebra crossing or libxing for barcode reading. That's all flavors of barcodes, the linear ones, the QR codes, that sort of thing. We use Tesseract, which is another library for doing optical character recognition, so if you want to read the text off something. We use Beautiful Soup to help us move images around, so if you want to, say, scrape Google image search to get like 100 pictures of cats, we have that sort of built in. We have Connect support using FreeNect. Unit testing library is Nose. We do some web stuff with Flask and CherryPy. We have a few demos out there using Arduinos with Pi4Mata, because generally as soon as you do computer vision, you want to do some sort of controller system to do something cool with a robot. Yeah, so why do we put everything in a super pack? Well, there's just piles of library, and we wanted to get you guys basically a baseline so you can see what's there, and then decide if you like it, and then if you like it, then you can actually deal with the pain of getting everything installed. And this is probably the most important slide right here. Where do you get help after this? Because I'm not here to teach you guys right now. I'm here to have you come and bother me and do cool stuff with the library and ask questions later. So the primary source to do for any sort of help is we've sort of rolled our own help site. Hopefully open up here. If you have any questions, we check this twice a day. We got an army of sort of students that also check it with us. If you have a question, there are no dumb questions. Feel free to come and just like ask us a question. If you have a problem, if you have an install issue that you don't get, you'll usually get a response within 24 hours. There's also, we have a full set of documentation up at simplecv.org. This should be, we need to re-roll it, but it should be pretty fresh. So if you need a resource just to learn about the library, you can always get us on Twitter. We usually respond pretty quick to that. We're also pretty regularly on the computer vision subreddit. So that's another good place just to ask like generic questions. How would I go about finding, you know, my dog's nose when he's looking in the camera? Or something, you know, just these abstract questions about how do you do something like that? On the printed page, we have Jan Erik. There's actually two Python books for computer vision now. There's ours, there's the Practical Computer Vision using SimpleCV, and there's also Jan Erik, who has another one that's more sort of NumPy and pill focused. Jan Erik was supposed to be here, he couldn't make it, but those are generally good resources. I have discount codes on the book. I'm not here to sort of sell books. The books are just the product of having lots and lots of good documentation and trying to motivate it. So why do a bunch of people in the Midwest sit around and write computer vision code all the time? Well, first it's because we really like computer vision, we really like Python, and we really like open source. But we're also trying to do crazy stuff disrupting basically quality control for manufacturing. There's lots of factories in the Midwest that use computer vision as a practical tool to solve problems. So we do stuff like, so this is a bolt manufacturer in Michigan. They have, they want to know what does the metallurgy look like inside the profile of their bolts? What are the parameters of like the fillet undercut of their bolt? Because if it's wrong, you could have cars that fail. So we help them sort of solve these problems by looking at images and figuring out what we can find. We also do a little bit of farming stuff too. This is a fish farm in Michigan. They're looking at, they want to know how busy, when their fish are moving. And this is great because it's one of these things. I own fish tanks. I would love to watch my fish and see what they're doing. But it really actually has practical applications. This fish farm sells fish. They need to know when the fish are hungry, how much to feed them, and when to feed them. All right. So that's all the pitch. Is everyone feeling like they have a virtual box, that they have everything about ready to set up? All right, so what you're going to do here is if you go, there is a folder in your VirtualBox. If you open up a terminal, I think if you click on the upper left-hand side, there should be something kind of up here, and you should be able to go find a terminal, and it should open up to your home directory, and you should be able to go to something like code, cd code, and you can use tab complete, code, SimpleCV examples, right? And then there should be a presentations folder in that. So you just, my system's a little bit different, but it should be something like that. So everyone see that? And what you're going to do is you're just going to run this command. So you're going to go SimpleCV notebook, which is telling SimpleCV to start up an IPython notebook. And then you're going to do -- pylab equals inline. And all that says is that we are going to do some rendering of figures. And we're going to use matplotlib, and we want them to be inside of our notebook and not have pop-outs. So once you do that, you should get something that looks like that. It'll pop up a warning message on the VirtualBox. It'll say, it might take a second. If you say continue, Just let it go for a second. It's a very big IPython notebook because there's lots of images in there. It just takes a second to load. Okay. So I'm going to stop there for a second, let everyone kind of catch up. So where do you write your code? So I just started up a notebook. So you can use SimpleCV in a regular Python file, just like you would with any Python file. You can use it in sort of a REPL, like in the Python REPL, or you can start an IPython REPL and play on that, or you can use the IPython notebooks, and that's what we're going to use today. I like these just because you get all your images and all your figures and all your plots all in one place, and you can save them and share them, and I think this is sort of the way of the future. And it gives you, if you're doing computer vision for MATLAB, which is where a lot of people get introduced to it, it feels a lot like MATLAB, except it doesn't cost $5,000. So it's nice. How does this fit into a workflow? Generally, IPython, the REPL, is really great for prototyping, figuring out how you want to do stuff. Once you get things kind of figured out, we usually move it to a web notebook where it's kind of testing if you're tweaking a little something, a little parameter, and want to play with some data. And then once you're ready and you've got something you think is working, you just put in a, copy paste it into a Python file, and you're good to go. So a note about the virtual boxes. They do not support USB cameras out of the box, so we're going to be working with static images, but I'll do a couple camera demos here so you guys can get a feel for what's going on. So I'll give you a really quick Hello World demo, right? So we just do up here at the top, we have our basic import statements for SimpleCV. We want an image, we want a display, we want to be able to show it. We're going to do some stuff with color, and we're going to do stuff with a camera. So we import those 4 things. We create a new camera object right here. We create a new display object, and this is sort of optional. You don't really need to do that. Create a while loop, and all you say is, camera, get an image, and save that to an image. You draw some text on the image, the classic hello world, and then you save that image to the display. That's it. And that will, I can just run that. I'll pull in my camera. And that's it. So this used to be a pain. It's generally pretty easy now with SimpleCV to start grabbing images off of a camera and displaying them, and at least be able to overlay text. And you can actually exit out of this using escape. So the reason that we use IPython 2 is that it has some really cool features that you can use to sort of figure out how the library works and to teach yourself about SimpleCV. So if you say go to your notebook and say you had a question about the image class, you can do question mark. Actually, let's do this in REPL. So I'm going to start up this Python shell. So if I had a question about, say, image class, I can just type image question mark. And here's my documentation. So if you guys can see this. So this basically summarizes the image class. We have an edict now that when we write any part of SimpleCV that there will be almost as much documentation as there is code. So just about every method should have a description of what it is, what it does, why it's useful, what the parameters are going into the function. I'm going to give you an idea of what is a good starting place to use them, what it's going to return, and give you an example of how to use it. So any method that you would want. So say, I want to say, I'm just going to create an image really quick. So there's a command called edges. So I want to know more about the edges method, right? So I can call this up and I see, okay, so I have 2 parameters, they're 2 thresholds. If I want more documentation, I can go here, the lower threshold, what it's going to return, and an example of how to use it. And maybe somewhere else that I would want to look if I wanted to do something similar. So immediately now you know that, like, if you only know that there is an image command, you now know that, or an image class, you know how to figure out what's in there. You also have tab complete in here, so you can do image dot, well, I know there's a find method for this, and I can pull up everything that you can find. So if you want to find lines or motion or circles or whatever, you can kind of query in that way. There's also, I'm not going to run it here, but there's a tutorial command. There's actually an interactive walkthrough in the shell that we've created. So if you want to get started that way, you know, if you go home and you're like, wow, I went to this great tutorial, but I forgot everything. It kind of fell out of my head. The tutorial will walk you through parts of that. So I just showed you guys how to open up the shell, or at least the interactive shell, the IPython shell. And like I said, question marks in front of everything. Tab completion to figure out what's in there. Another cool feature is that you can use the up arrow to get back to your previous commands, if you're not familiar with that. You can also use what they're called IPython magic commands. These are really helpful. So if you have a piece of code that you found on the web and you want to copy it and paste it in, sometimes the formatting's a little messed up. So you want to be able to you get the tab straight. If you use the %sign paste, it'll actually put formatted code back in the REPL. So I want to show you guys just again the sort of hello world that we did before with the shell. So I'll go back here, and I'll start up SimpleCV in the shell form. And I can say, here, give me a camera. .640 by 480, give it a nice little display. Okay, and so I'll create a while loop. Is not done. Cam.get the image and save the image to this display. And there we go. So this is just me running at home, and you can start adding stuff on right away. So all SimpleCV commands sort of build upon each other. Most of them actually return a separate image, so you can string them together. So if I want to get an image, get its edges, invert it, do an operation called a dilate, you can start stringing stuff together like this. And then you can let's try this. Cam, image equals camera, get the image. So you can string things together really quickly. So that looks like that. All right. So one last thing. The reason we're focusing on IPython web notebooks for the tutorial is that they give you essentially the best features of an IDE and the REPL. So you're able to edit code. As you saw me there, it's hard to edit code sometimes in that REPL loop, but you can do that really simply in the notebook. But you also get this sort of immediate feedback. So it's a nice intersection. However, so in the notebook is really easy to start, like we've already mentioned. So you do SimpleCV notebook, and then the PyLab inline. The PyLab and inline are both optional, but those will get you matplotlib, which is a pretty useful tool. And And it'll immediately take you to a dashboard that looks like this. And here you can save all your notebooks. You can have multiple notebooks. They're all relative to the directory that you started Simple CV in. So if you start it in your home directory, they'll be there. If you start it somewhere else, it'll pull the notebooks that are immediately there. Okay, so when you're using the notebook, it's essentially the same thing as I've just shown you in the shell. All the magic commands should more or less hold the paste, the question mark. The one thing that kind of gets people initially is that instead of doing a return gets you a new line, a shift-enter actually will execute your code. So that looks like this. So here I have basically, make sure I want to get in the directory. So I execute that. Okay, so now I'm in this home directory. And say I wanted to create an image, a static image that's in that directory. I have this hello world.jpg. I also have a copy of that up on the web at some web address. So I've actually, you can actually give Simple CV as a command to create an image, a link to any image you find on the web, and it'll just do the curl, pull the image down, and open it for you. And you can then use the show command, especially in Notebook, to just show you what was there. So that would look like this. And here's a swoot. So you see this first version I kept locally is kind of big, and then I took the smaller image from the web. There's also we keep a couple built-in images, which are handy for testing. If you just have an idea, you want to kind of see how a method works. There's Simple CV, which is just our logo. There's also Lena, who's this classic, through the ages, has been in like every computer vision paper and image processing paper ever. So we keep her around. It's just a classic. It's interesting because it's just a piece of history, and we built it in just so you can test images, because every sort of filter, every sort of process you've ever seen relies on this image. So once you have images, you can actually start saving them and doing stuff with them. So there's just a couple things you need to know about IPython notebooks before we get really busy. They're still a little bit early. There's some features that they don't have that you'd really like. There's no autosave yet. So with the notebook, get in the habit of executing something or saving before you execute it. Just Control-S and then Shift-Enter, because they won't save automatically, and you can lose work that way. Another note is that if you edit a module, say you pull in some library that you wrote, and you notice a bug and you go and fix it, you have to restart the IPython kernel, which is just in a little submenu in the IPython notebook. There's minimal editing support, so there's no find and replace yet, which can be a little bit of a bug. And sometimes it's still just ever so buggy, but it's usually pretty good. Large images, especially when you try to display them. If you have like a full-size DLSR image and you try to show it in the notebook, it doesn't really like it. All right, so we've shown you guys basic image loading. Basically, we can pull down anything off the web. Most of your standard image formats, GIF, JPEG, bitmap, PNG, those are the big ones, WebP. I think that's probably the majority of them. If you have JPEGs that are, say, coming from your digital SLR camera, there's actually a method, too, where you can pull out the EXIF data. So if you want to know the GPS coordinates or the exposure settings or whatever is sort of contained in your camera's EXIF data, it's really quick to pull that out. So you can save an image just by using the image save command. Image save by itself with no parameters will save images to a temporary directory. This is useful if you just want to quick grab a bunch of stuff. If you tell it to save a specific file, you give it one parameter. Say, save this as image1.jpg, it'll convert it to a JPEG. If you say, save image1.png, it'll save it as a PNG. You can pick whatever format you want, and it'll try to cajole the image into that format. There are also a couple parameters flags. So if you, say, have a task where you want to compress an image, like say you have a bunch of really high resolution images and you want to make them smaller so you can toss them on the web, you can set a compression flag. So if you want to write a little script that scrubs a directory and tosses it on the web and shrinks all your images down, super easy. You guys, is everyone following along? Is everything going well so far? All right. Yes. Oh, everything is, so we have a simple CV regular GitHub repo. There's also a examples repo and education repo, and it's all in there. The notebook, the slides, all the test images, all the example files, all of that's there. And, yep. We would find it. Here, I'll show you right now. And I can also send it out after class. So that's going to be at it'll come up. Simple CV, so it's Ingenuitas, and then it's simple CV examples. So all of the course material are there. If I make any changes to this, I'll commit it. I'll probably actually expand upon this lecture more too. So as we add new stuff, as we add new features, it'll probably go in here. All right, so I think we're about ready to start doing. Is everyone feeling pretty secure in having things set up and ready to go? Oh, the path?
Yeah.
Sure. So it's going to be, well, here, I'll just put it up there. So it's going to be code.
No, URL.
Oh, the GitHub URL? Sure. Ingenuitas / simple CV examples. Okay, so starting out, if you're not working with raw images, you're going to be working with some sort of camera, right? So generally, most consumer USB cameras should work with simple CV right out of the box on most operating systems. This is not 100%, but there's a lot of cameras out there. But most USB cameras should work. The only camera parameter that you should really care about most of the time is the camera index, which usually is associated with the order that you plug cameras into your system. So if you have a built-in camera, it'll usually be at camera index 0. If you plug another camera in, it'll be at camera index 1, and so on. Some cameras have properties that you can set, like if you want to set the resolution, if you want to set the exposure, if you want to set the gain. This is sometimes supported. This is all vendor specific. So there are utilities, if the camera is supported, to do these sorts of things where you can change them. We have a list actually up on the main Simple CV repo that lists some of the cameras that we use that we think work well. Just about every camera object will have a camera.getImage function, which just returns the latest image. And that will get you, most of your work out of your camera. Cameras also have properties. You can just get all the properties that the camera features, at least see what it's using, and you should be able to set individual properties and get individual properties using the camera.get property and camera.set property. So in addition to cameras, we do have basic Connect support. It works pretty well on Windows. I've used it on Mac. I've used it on Ubuntu. We use the FreeNect library. That supports sort of the basic get image object, right? So you can get the RGB regular image, and then you can also get the depth image, which we can artificially color. So that's telling you how, not only what the color image looks like, but how far away something is. There's something called a JPEG stream reader, which is basically useful for IP cameras. You can now get these consumer IP cameras that cost like $100. So you can also, this is a really cool feature, most Android phones you can get, if you have an old Android phone sitting around, you can get an application that makes your phone's camera into an IP camera, and then you just put it on your network. So what you end up doing is it'll use what's called a JPEG stream. If you point the JPEG stream reader to where that camera lives, it's basically its IP address and its port, it will say, okay, it'll start pulling images down, and you can use it just like a regular camera. Actually, if we have a little bit of time at the end, I'll show you guys how you do that and how you can play with that. But it's a really handy feature if you want to have remote cameras and you don't want to wire stuff up. You can use virtual cameras. Yeah?
Sorry, you might have said this just a minute ago, and I'm sorry, I can't repeat. Do built-in cameras in notebooks typically manifest as USB cameras?
Yes, they almost always, and they're usually at camera index 0. Usually. Now, I know for a fact that most Macs and most like Lenovo laptops which we run are pretty good about that. I've seen some weird laptops where that's not the case, but that's the majority of the time what happens. There's a virtual camera class, which we basically treat video files as virtual cameras because you want to use the same interface. You want to say a video is really a series of single image frames, and you want to be able to go through them linearly. So we treat video files like a camera. So you create a virtual camera object and you pass it a video file. Video support is not something we do exceptionally well right now. Usually raw AVIs work really great. This is all going to be subject to what your codecs are on your machine and how you have that configured. So just briefly, other cameras that you can use, we regularly use document scanners for certain projects. So any libsane compatible document scanner you can use as a camera. So you can actually just say, scan this, and then find some data from it. And you can set resolutions and ROIs. This is really handy if you have images and you want to measure stuff, because you know precisely what the camera's DPI is from the start. So you know if you find something that's 10 pixels wide, 10 pixels times your DPI is going to you'll be able to figure out how big something is. Digital cameras like DLSR cameras, we use the Piggy photo library, and you can kind of get a preview image because most of them are so high resolution. You can get a preview image from them, and then you can get a full resolution image. And this is an optional library. And then we also support some basic machine vision cameras. These are sort of high-end industrial cameras. And these are really nice if you have a sort of professional application where you need fine-grained control over, say, your camera's gain or your camera's exposure or something like that, or you want interchangeable optics and high frame rates. Okay, so now that we've gotten where to get data for, I want to talk about one sort of data abstraction we work with images. So you have single images, you have cameras that give you images. There's also in Simple CV this notion of image sets, which are big collections of lists of images. Image sets are really good because they can be like a segment of video, like say a second that you want to process. They can be a whole directory of example images if you want to train some sort of classifier. You can pull down an image set of, say, just a regular old something that you want to find off the web. If you want to find every picture of cats, you can create an image set and say, hey, download cats for me. And then you can do some operations on them. Oops. So I'm going to show you guys an example of that. So if you go to your notebook, and we've basically tracked through these first couple sets here. So if you guys want to, so you can either go into the notebook that I've provided and hit enter and just sort of say, yeah, it works. Or if you want to rewrite code sort of interactively and see what's going on or modify it, please feel free. So what this is going to go on here is that you're going to have a set of images. I'm going to create an image set just by using the image set command. And I'm going to tell it to say, download something. I'm going to tell it to download cats. And then you can take that set of cats and I can get it, just show me what you got. Really simple. So just these three commands will give you, if you hit Shift Enter, will give you something like this. So now I have basically a Python list of images of cats that I can go through and do something to. So there's sort of set-based processing. So I can go through the images of cats and I could take the average of every cat. So I take all my images, I smash them down into one big image, and for each pixel, I take the average. So that ends up looking like something like this right here. So this is the aggregate of 10 cats randomly downloaded off of Google. For image searching right now, it is. We have utilities to push up to Flickr. We should be able to search on Flickr tags really soon. There's also a couple other like computer vision oriented resources for finding image sets, but generally this works pretty well most of the time. You can access, so I have my average. I've shown you my average cat. I can also access and get into image sets just like I would a regular Python list using the bracket notation. So if I want the fourth image of cats, which is from 0, 1, 2, 3, I can just go, give me the third cat and show it to me using the show command. If I want to make all the images the same size, I can use the standardize command. So I can say, make all my images 128 pixels by 64 pixels. This is useful if you want to push them all together. Say if you wanted to make, I don't know, an animated GIF. So you can do that. You can resize the entire set. And then I can take an image set and I can save it individually by using the save command. Or if I give it a single GIF parameter, it'll smash it into an animated GIF file. So I can show you what that looks like. I think. Let's see here. Import. Wait, that's not going to work. Now, this will actually pull up image. File, open file. So you can smash those all together and do something cool with them. So if you have, like, if you just want to show a sample of some processed video to somebody really quickly, this utility is actually kind of handy. And then the other way that you tend to use image sets is that you iterate over them, just like you would iterate over any Python list object. So you can just say, for a single cat image in my set of cats, take the cat image, apply some sort of processing to it, like binarize it, make it into a black and white image, and show me the results. So that is going to look like this. So I took the first image, got a black and white cat, second image, and so on. Go back to the slides here, and you can see all the slides have repeats of what's going on in the actual processing. All right, so we're going to move from taking sets of images to actually looking at individual image operations. So on any given image, you have you have a list of pixels. You have x pixels wide by y pixels tall. Pixel counting always starts, and this is a generally beginner mistake. It always starts in the upper left-hand corner. So at the upper left-hand corner, you have pixel 0, 0. At the bottom right-hand corner, you're going to have the width and height of the image, and all the pixels in between. In Simple CV, we treat these images as two-dimensional arrays of color tuples, where the color tuples give you the R, G, and V values of each pixel. So I'm going to show you guys just a little bit about how we work with slice notation to get at certain things in the image. So if we go back over to the notebook. I have a little sort of hello world here with getting at pixels. So we're going to start by opening an image. If you guys want to follow along, there's a hello world image, which is just this image of toast right here. If you want to see just the first color value of the first pixel, right? So we'll see what that is. So the first pixel, right, has a color value of 102, which is the red channel, 67, which is the value on the green channel, and 37, which is the blue channel. And these go normally on most images from 0 to 255. You can also use a get pixel command versus using the slice notation. In the slice notation, the first value is the x value, the x pixel location. The second value is the y pixel location. If you want to get something slightly larger, you can use the slice notation to go look through a chunk of the image. So this line here, you guys can see that, right? You can go from, say, the 200th pixel to the 300th pixel, and then on the x side, and from the 200th pixel to the 300th pixel on the y side, and you can create a sub-image. And this slice notation will return a simple CV image object, which then you can go and further modify. So like, say, you could get an image that looks like this little piece down here. Oops. And if you wanted to process that more, you could certainly go ahead and do it.
Sorry, where is this directory on the VM?
You want to go to code, and I think from the home directory it's code, simple CV examples, presentations.
Why is it returning a float on the
The float value, I think, is artifact of coming from what we'll do, right, is we keep an instance of the NumPy representation of the image. So we'll return that, and that is actually storing it as tuples of floats. Because there are calculations, in computer vision, you're going to periodically travel between having like unsigned 8-bit integers and floating point numbers for certain calculations. So we tend to cache things and keep things in a sort of NumPy representation. I saw a question back there, too.
I was just wondering, the Stillman, when I run something like this, is like kind of crazy. I was wondering, is that from image processing? Is that from
It's a little bit of both. The VMs are really constrained in terms of their size, in terms of resolution, and part of it is just displaying the images. It's, even when you do like even PyLab inline, it's pretty smooth, but having that large sort of thing where it's trying to center it, it gets a little jerky. But we do like them because they keep, if you want to see things in series and see a progression of what you've done, it's nice. So, like I said, we did all this slice notation. I can see this new image that we created. I can also create another test image where I say, give me all the rows from 50, all the X values from 50 onward, and give me all the Y values. And that would create this image, right? So this is going to be our second image. So it's just basically a little crop value. I can also take a very small image, right? So I can go from 0 to 5. Or if I just want to get the raw NumPy array, I can say, hey, give me the raw NumPy array. And that will look something like this. So here, this is a 5 by 5 image. So this is the first pixel, this is the second pixel, this is the third pixel, and so on. So if you had just a small area you wanted to process by hand, you could do that. So you can use these slice notations to actually get at values, or you can use them to set values too. So here, I'm doing a case where I take from 0 to 105 in the X pixel direction, 0 to 105 in the Y pixel direction, and I say, make this the color red. And we're using the simple CV color class, which all the colors that you could probably want are just all uppercase notation. So that will return something that looks like that, right? So this is basically moving pixels around. How do you set them? How do you get them? What do you do with them? So we'll go back over here. So like I said, images are, for the most part, read-only. Oh, sorry. Yeah.
There's two bits there. One is that you set the color red of the straight on the image, and the other one is you get NumPy, and then you set the color red. One of those is wrong. This is what's at least in the example here in the notebook. It says like if you just do image from 0 to 105, color red, and so that's wrong. But then if you say that's get NumPy, that's right. I wasn't sure that's how that.
Oh, yes. So generally, if the process, the way we do these things generally, right, is that you always return a new image that's been processed. So you keep the chain of images that got you to a certain point. So generally, you want to keep with that sort of way of doing things. Now, you can get around it. Sometimes you're trying to do things fast or conserve memory, and you want to do that. But we generally try to look at it as, give me the chain of processing. NumPy values can be big, grabbed via, So once you get if you want to get the raw pixel values, you can use the get numpy. There's also get gray numpy. There are a whole host of get functions that return either numpy values, OpenCV values, basically that will change the image format to something that you want to use for a particular task. You can get at individual pixel colors by just adding a third level to the slice notation. So you have bracket X, which is your X value, and then Y value, and then the RGB value, 0, 1, or 2. It's helpful to know that all the images have a width and a height parameter that let you know how big they are. So if you want to set your slices and figure stuff out, it's usually pretty easy. So I'm going to move back over here. And we can look at sort of another example where we're processing images. So what I do is we're going to create the same image, this hello world, this sort of burnt toast image. I'm going to get the gray and the colored numpy images. And then I'm just going to print the width and height so I have it for reference. In this case, it's 640 by 480. I'm going to modify these just to show some image editing, right? So I'm going to go from X value 20 and then all of it. So that's going to be the entire top of the image, right? So from 0 to 20 and then all the way across. And set that to blue. I'm going to take the other side of the image. I'm going to go from all of the X values, but only from Y, from 0 to 20, and hit that as green. Take a small square of it, set it to yellow. And then I'm going to use this really slick NumPy command called where lets me pick parts of the image that meet a certain criteria. So if this is a gray NumPy image, right, it only has single values. It doesn't have RGB values. So I want to say all the pixels that are brighter than 230 return their XY locations. So then I can take those XY locations, I can zip them, and then I'm going to do a for loop, and I can actually set them again in the new image and set them to red. So I'll show you what that looks like. So does that make sense? So in the gray image, you take everything that's really bright, everything that has gray values above 230, because 255 is going to be perfectly white, 0 is going to be completely black. So I'm going to take everything that's really bright, find the locations of things using the where command that are really bright, and set them to being red using that small list. Oh, and then I'm going to actually take that list, because it's a NumPy array here, and shove it back into an image and show that image. So I just say colored, which is colored is a NumPy array, a two-dimensional NumPy array, and put it back in the image. And say save. And then for another example, just showing the indexing into the color channels, right? So I'm going to take the entire image here, all the X values, all the Y values, and then the third channel, which should be the blue channel, and I'm going to set every blue channel to 255. So that means the blue value for every pixel is 255. I'm going to create an image and toss that NumPy array in, and then I'm going to show it. And that looks like this. Does that make sense? Is everyone following along? It's clear? You guys get excited. It's not that early. Things will get cooler here. We're getting the basics in. All right. So we'll go back to the slides. And we did this all really quick, but, it's not that much code to actually do these sort of manipulations. And finding, areas of brightness or darkness and changing them are really, really common tasks in computer vision. And we'll get into why here, but so the next set of things, we just use slice notation to do really the hard way of cropping stuff and scaling stuff, or cropping stuff and getting sub-images. But we have methods baked into Simple CV that make this easy. So instead of saying, give me from pixel 10 or pixel 20 in the X direction and pixel 10 to 20 in the Y direction, you can just use a crop command. And you say, usually for crop, you give it the upper left-hand corner, so the smallest values, the min values, and the width and the height, and it returns a new image. Sort of along with crop, the basic sort of functional things you do are scaling images. So I have something that's tiny, I want to make it twice as big, scale it by 2. Want to make it half as big, scale it by a half. There's also resizing, so hey, I have this image, it's 320 by something, I want to make it 640 by something else. Most of these methods, like resize, will, if you give it one parameter, like say I want to make it a certain width, it'll figure out the height that you need from an aspect ratio. We try to make things intuitive that if you give them one parameter and there's something we can infer, we'll infer it. There's also some other basic rotational stuff. So you can say image.rotate, which will rotate your image. We like to keep things easy and intuitive, so we tend to use angles for these things versus radians. So rotating at 90 degrees will rotate at 90 degrees like you'd expect to the right. For rotations, there's two parameters. There's a second parameter, which is called fixed. The default behavior is to rotate and keep the same image size. So it's like you have it's like having a picture frame and a picture, and you rotate the picture but not the frame, because the picture won't fit in the frame. Or you can rotate it, not fixed, where we'll just get you a bigger frame and put your image in there and it'll be rotated. There's also flipping commands, which is something you're going to end up doing with cameras. Sometimes the way camera buffers work is that you get something that's upside down or right side up, and you can do flips. What's worth noting here, and this is another really common mistake, is that flipping is not rotation. Flipping is completely different than rotation. Flipping is going like this, and rotation is going in a plane. So you can't flip, and think that you're going to get the same image as you would if you rotate. One other quick sort of image moving process is something we call blit. And blit, it comes from an old computer graphics term. It means bit block transfer. It really just means copy and paste a bunch of pixels from one place to another. So blit takes in basically another image as an argument and a position where you want to put it. So if you have 1 minute image and I want to blit it here, you can blit it at 1010 or some sort of parameter down. You can blit it up here and we'll return the image that is just the other one on top of it. You can also use blit with binary masks, so a black and white image, and you could say, blit this image, but only do the parts that are white in my mask. And I'll show you what that looks like in a second. You can also use an alpha mask, which is a grayscale equivalent, and you can also use an alpha value, which is just a scaling value of like how much from the image that you're putting in and how much from the image that's on the bottom. Okay, so let's take a little bit of a look at how that works. So we'll start by loading up this image here of Richard Nixon, right? Thanks for royalty-free images. That's great. Now we'll see. I went through and kind of manually figured out where his face was. So I'm going to crop out his face, and his face is going to be at 150 down, or 150 over, 190 down, and then it's roughly So I figured out where the other corner was and I subtracted off. It's roughly 150 wide by about 100 tall. Width, height, yes. And I can show you what that cropped image looks like. So here it is. Nice ugly mug. So then I can rotate it by, say, 45 degrees. And I'll show you the difference between the regular rotation and the fixed rotation. So here's the regular rotation, right? So that's like I have a picture frame, and I rotate it, and I keep the frame, right? So it crops it off around here.
You lose the corner information.
Yeah, we keep the same buffer size, so we rotate it in the buffer. And it's also worth noting that the rotation is about the center of the image. You can center your rotations arbitrarily. And then this is with the fixed equals false. So this just rotates it and gives you it so that you have the whole thing. Okay, so now that I've rotated it, say I wanted to make it smaller or make it larger, I can use the scale parameter. So I can scale it to half its normal size. I can scale it where I take the width and I scale it to half the width. And I don't give it a height parameter. I could give it a height parameter. And then I also just do a horizontal flip just to show what that kind of looks like, right? Oops. So here's the scaling, the flipping. So now that I have sort of a set of flipped and rotated Richard Nixons, I can say I want to reapply them to the original image and make something look kind of interesting. So the first image here, I'll take my source, the original big full photo, and I'll use the blit command, and I'll take the face, and I'll flip it horizontally, and then I'll put it back to where I got it from. So I say at position 150, 190. So this will be the first one back here. So that's what that would look. You see that? Where he, let me bring this up just ever so slowly. Right, so it's flipped horizontally. So realistically, this should be over here, and this should be over here. And it's been placed back. You know, and then so for another one, I can flip it and I can give it an alpha parameter of a half. So I'll take 50% from the source image and 50% from the image I'm putting in there and put them together. Oops. So that's a little bit more subtle of a result. You see how it blended the colors. That's because of the alpha value. So then we can start trying with the mask, because that's, you can see these edges down here. You can see the edges right where the face ends, right? So we want something that might be a little bit more subtle. So maybe if we use a mask, we can get that subtleness that we would want. So I create a mask using the draw circle command, which is something we'll get here to in a second. I just say create a circle that's half the, set it at the width of the face and the height of the face, or halfway in between. Make it 70 pixels on its radius. Give it a color of white, and if we scroll over here a little bit, make it filled in. And I create a mask. So that mask ends up looking like that. There's our mask that we're going to use to blit the face in. And, oops, sorry, I have scroll problems too. You draw the circle, you apply the layers on the mask, and you put the mask in using basically the same command as we used before, but we just set the mask equal to the mask we just created. And you will get something like this. So you see, now I've rounded it out, I have this mask, so I'm only flipping right here. So, which is interesting because there's so much symmetry in the face, you can actually kind of get away with that. So after I do the sort of blitting with a white circle, I'm going to go and make this crazy mask that is not just a circle. I'm going to take the image itself, figure out where there's interesting stuff, and use where there's interesting stuff to create a mask and blit in from there. So I'm going to use this command, and we'll get here in a second. I said, take the face, make it a black and white image, binarize it, and blur it, and show it to me. And then use that face mask as an alpha mask. So instead of doing black and white, do grayscale. So that's what the mask would look like. You see, so here's where we're going to transfer image, here's where we're not going to transfer the source image, and gray is some value in between. So that ends up looking like that. So is this at least reasonably clear? Do you guys have some questions? Okay, apply layers, and I got a slide here, we're just about to get to it. Essentially, we treat anything that you render on an image kind of like a layer in Photoshop, where it sits above the image so it doesn't get processed until you actually say process it. So you have to apply the layer, and then you can actually use it. It's only shown to you, it's not actually in the image buffer. All right, so does that make sense to everyone? Is it interesting? Okay, so here's our results. So I'm going to throw in a few more commands to you that we kind of hit on here. I used a blur command, which is essentially a Gaussian blur. There's a lot of other forms of blur than your regular Gaussian blur, and you can check those out in the documentation. And all you do use that for is to smooth out edges. There's also a smooth filter where you can get, like, say, a median filter or other forms of removing noise and leveling out images. There's an image to gray feature, which basically converts a color image to a black, white, or grayscale image. There's a threshold feature, and what a threshold is you say, in the grayscale representation of the image, everything's going to be from 0 to 255, where 0 is black, 255 is white. You set a threshold and say it's 128. Everything above that threshold we will set to 255, and everything below that threshold will set to 0. So I'll take a gray image and basically make it into this black and white mask-like image. And then you can use something like invert, right? If you did it backwards or you're more interested in dark things, you just invert it. So you take everything that was black and make it white, and you take everything that's white and make it black. And there's a grayscale equivalent too. So the other thing that we need to be aware of is how do we draw stuff? Like we just drew a circle mask on something. And like I said, each image treats the mask as a transparent drawing layer. And every time you call a draw command, it draws it on this transparent layer. And when you show it, it'll totally, SimpleCV is smart enough that it'll say, okay, I'm going to show you that. But if you actually want to save the image with that stuff on there, you have to apply that layer. You have to take all the rendering stuff that was on there and push it in to the image and then save that. So you use this command called apply layers, where then it puts it into your image. So now if you say looked for, say if you draw text and then you say apply layers, you can go and find that text in the actual image. There's also a clear layers command, which just will get rid of all the layer stuff. You can access the drawing layer directly by just using this sort of quick command called drawing layer, or DL. And it's worth noting that the drawing layer is actually a stack of layers. You can actually create more than one if you want to have more than one level of transparency. You can set an alpha value for them. And you generally, if you're accessing the drawing layer directly, you can get a little bit more fine-grained control. You can use sprites and do blitting, and sprites are basically little tiny images. So that's sort of the drawing high-level stuff. More so for you guys, how do you draw simple stuff that you want to do in an image? There's a draw circle command. There's a draw rectangle command, and circle takes basically the center of the circle, the radius. Drawing a rectangle takes the top left corner and the width and the height. You can draw a rotated rectangle, which is just a rectangle that you've shifted and rotated, and you do that by giving it the corner points. You can draw text, so if you find something, right, you say you want to write hello world, you just draw text and say hello world and put it the top left pixel at wherever you want to put it. You can draw lines, so if you find a line, it goes in, and then you can also draw points, which is just put a circle around a particular pixel. All right, so I have just a really quick example of drawing here. And this is mainly to motivate doing some more extensive stuff. So I create this little polygon, right, that goes from these pixel coordinates. And I can take that polygon, I can color it green, I can fill it on, and I can put it in our drawing layer. I can also create this polygon and move it around. So basically, I do this little list here where I say, create a value called I, and go from 0 to 90 in steps of 9, and I add I to each point in my polygon. And all that has the effect of doing is moving it down like that. So here's an example of draw rectangle, just the XY location and the width and height, and I set the color to be black. The width, generally we either use width or thickness. This is not consistent, so we're going to fix it in the next version. We set it to -1 for filled and set it to 1 to be some sort of trace outline. And you can set the alpha value on a lot of these things. So then I draw a few more circles, a few more lines, add some text like, say, hello world, and then I can show you what's going on, and I can apply these layers and save them. So that ends up looking something like this. So you see basically the polygons being rendered, the lines, the circles. This is the way that when you process an image, you want to be able to say, here's what I'm looking at, here's what's interesting, and this is how you kind of call out what you're interested in. And so you can also want to say clear layers, get rid of all this stuff and start back over. All right, so this is all the introductory stuff. Was that clear or kind of clear? No questions? Feel free to be loud. Okay. Too fast, too slow? You guys want me to speed up? No, okay. I just want to check that everyone's still paying attention and still interested. All right. So now we'll start doing some interesting stuff. All right. So let's really quickly talk about color spaces, and color representation. So the general problem of computer vision is that you have massive amounts of data that you have to distill down to one answer. So you have a 2 megapixel image where each pixel, right, has 3 bytes in it, red, green, and blue. And you want to, 3 times a second, distill all that down into one answer. And that's where the problem is kind of fun. You have piles of data and you're trying to get down to one answer. And part of how you do that, right, is you start lopping off stuff you don't need. A lot of times you don't need color. So you just get rid of color, you move to grayscale. Sometimes you don't even care about grayscale. You can do everything in black and white if you pick your black and white correctly. So moving from color lets you get rid of bits really quick and get down to an answer. And that's what's kind of cool about it. And the other thing that's interesting is color is really, really hard to represent. So you see over here on the left, right, this is the visible spectrum, right? So this is every color possible. Each one is a different wavelength. For your eyes don't actually pick up on every single one of those wavelengths. You only pick up on 3 of them. Or you kind of have this response function, right, that maps this to the set of like 3 sensors that you have in your eyes or in your camera. And it's imperfect. And then you take what you've mapped to your sensor and you try to push it on to values between, 3 values between 0 and 255. So this mapping process is like really, really imperfect. Color is exceptionally hard to represent. And it's actually surprisingly hard to represent. So just to give you an example, and this will mess with your mind a little bit, where in the visible spectrum does that flower's color live? Can you point to where you have magenta flowers? It's not a spectral color. Your brain is incapable. I mean, your brain is faking you out because there is no place where you wrap the red part of the spectrum back to the blue part of the spectrum. It's a line. It's not a circle. You can't do that. So magenta doesn't exist in nature, but it's a color that we create and we represent and we see it. So, that's part of the difficulty in these problems is that you're dealing with something that's just not real or is a very poor representation of the real world. To fix part of this, what you end up doing is you end up moving between color spaces. So certain color spaces, when I say color spaces, there's the red, green, blue that I think most of you are familiar with, right? There's gray, we've talked about gray, right, which is just one color, brightness. You can also use something like HSV, where you have a hue, which is the pure color form, right? You have a saturation, which is how much color you have there, and then sort of like a value, like how well illuminated it is. And each of the color spaces sort of try to pick out different ways of representing light. And sometimes it's a lot more useful to look at hue, which is to say, I don't care how well lit something is, and I don't care how saturated it is, I just care about what color it is. And if you approach problems like that, you end up doing things a lot quicker. So in HSV space, which is going to be the primary one that you're going to want to switch to, you use hue values, which go from 0 to 180. In simple CV, yeah? RGB is because, well, it's partially because of how we structure our cameras, right? You can represent RGB by putting little lenses inside your sensor, which break out the colors and then they go to the sensor. So it's easy to extract that information. That's how your brain sort of does it too. Like you have rods and cones, and they pick up on those colors. But this is a better way to think about the problem versus how it's better to use RGB in actually acquiring data, if that makes sense. So to move between the color spaces, right, you can, in Simple CV, you can just use 2HSV or 2BGR, which is just flipping channels. There's a few other ones. HSV is going to be the primary one that you're going to want to switch to for most simple applications. There are a couple like YCR, CB, which we use for a few things, but you usually pick a color space because it's advantageous to work in that color space. And primarily for simple stuff, you use hue. And you use hue because you can look at, say, stuff like the peaks of hues. So if you have an image, right, and there's something that's big and red in it, you can say, find the red thing by looking for the big peak around the hue of red. You can also sort of segment the image or break it up into chunks by saying, I have this color I know I'm looking for. I'm looking for the hue of red or the hue of some greenish yellow. Now tell me how far away every pixel is from that color. And then you can also just visualize what the hues are. So you have like a rainbow, right? You have from like red to purple. And you see where the hues are most are biggest, and that's your primary tool for figuring out an image. So here I'm going to show you guys an example of how, even though you can't actually point to where on the spectrum the purple flower lives, how you can kind of use hue to get at it. Oops, sorry. All right, so I'm going to import PyLab as plot, and this will just allow me to plot some histograms and stuff, to see stuff. Then I'm going to open this image that's in your image directory called flower. And it's just that flower image I had before. It looks like that. And then I'm going to call this function called huePeaks. And huePeaks just basically returns, it finds the peak, the highest color response in the histogram of hues and returns the hue and it's basically its response. So that would print something that looks like this. So we know we have, I think this is a normalized bin count. We know we have a hue peak at 35, whoops, at 52, at 140, and 166. So the hue values go from 0 to 180. So I don't have a really good way of showing that, but let's go down here to this plot. Matplotlib will, for some reason, plots after the image rendering. So these are the peaks that huePeaks found, and I just plotted them for you. So there's one here at 166, which I'm going to guess is our flower, right? Because if it's purple on one side, purplish blue on one side, and reddish on the other, purplish blue is going to be over here, and it's also the biggest thing in our image. So I can also kind of infer that this second peak, I think it's going to be, well, red, orange, yellow, greenish maybe. So this is going to be probably some of the background. So what I can do is now that I have those hue peaks, and I've plotted this histogram of the hues so I can kind of infer what's the biggest responses here, I can say take the third value, the third peak that I found, which is going to be 1, 2, 3, it's going to be this 166 value. Sorry, it's the fourth. Take its hue value, and I'm going to use this hue distance function. And I'm going to say, tell me how far away every pixel is from this hue color. Yeah?
On the histogram, what are the units on the y-axis?
The units on the y-axis, I think, are normalized to the maximal value. I'd have to double check that. It's probably something that's close to unitless. It's probably unitless. I'd have to think it's probably normalized. I'd have to double check, though. It could be the HSV, because you have like a 3 space, you have a 3-dimensional space. It could be the distance too, but normalized to the max. So anyway, the hue value, right? When I say this hue distance, it actually returns another image. And the farther away a hue is, the brighter it's going to be, the more white it's going to be, because we're mapping how far something is away, not the color. So when I do hue histogram on this color, right, we see that, hey, this flower is really, really close to the color that we just gave it, or the outline of the shape of the flower is really, really close. Everything else is really far. And this is really useful because what we can do, right, is I can say, take this image, make it a white blob, or invert it. Make everything that's black white, and make everything that's white black. Because that's how we kind of frame questions. And I say threshold it. Give me all the colors that are above 220, and just return a black and white image. And save it as this image binary and show it to me. And what you get here when you do that is this image. Right? So now I've basically gotten the full outline of this flower. Right? So if I wanted to say, cut out this flower and put it in another image, or create a catalog of flowers that I found based on looking at hues far away from green and then do some machine learning on it, it's fully, you know, I can do that. I can do whatever I want because I found the outline of the flower. So I'm going to show, so we're going to go back. I'm going to show you how to do a few things with gray. I think we have to have a break at 10:30, is that right? Sure. So here we go. Here's the original image.
Yeah. So we get the 2 peaks, but what about those dark shadows? How did it know that it's not a different color?
Okay, so we only, when we generate this image, right, this image is, so it's grayscale, right? So we only have one channel. So it's working just on the hue channel of the HSV space. So all it's saying is color. It's not saying, it doesn't ask any questions about illumination or saturation. It just says color. Does that kind of make sense?
They said even though the shadowed areas are still that color, even though they look dark.
Yeah, because you're working on hue. You're not working on illumination. Yeah. 1050? Okay, cool. So we can charge on a little bit. Does this kind of make sense how you would frame this question? Okay. All right. So we just did this in HSV space, which is the hue saturation value space. I should go back to my slides. But we can also repeat this in the grayscale space. So color is important sometimes, but sometimes we just care about light and dark. A lot of times you just care about light and dark. So you can use the 2-gray method on a color image to make it a grayscale image. And then you can say, if you want to find something by looking for light things, you can adjust the contrast of the image, right? Yes?
I have a question about you. So how do you, I kind of understand what you're saying, but how do you tell that 2 colors are different? Because when you're talking about lighter or darker shades of color, it almost seems like there'd be a point where they converge, but if you're not counting the lightness or darkness, right?
Here, maybe this will help. So right, you're basically mapping colors to different points, right? So if you think about RGB as a cube, right? And this is sort of exaggerated because, right, way down in this corner you have bright white in that far corner, and way up here you have, way up here you have white, way back there you have dark colors, right? And everything else is represented in between. So if you want to say find things that are red or around a certain color, you have to carve out a little bit of space in that cube like that. Whereas when you use a representation that's supposed to be kind of like this, right, where you're using sort of the cylindrical coordinate space. Does that make sense? So instead of having a cube, we have this half cylinder. Okay, so your hue value, right, is your angle here, right? So that's one dimension. That would be one channel. That would be like your R value in RGB. There's this value channel here, which is like basically this how dark it is, which is another channel, which would be like your blue channel in RGB. And there's the saturation, right, which would be like your G channel in RGB, right? So you say, basically you say, I don't care about this. I don't care about this. I just care where on this wheel this lives. And in that wheel, it can be any sort of darkness or lightness that you want. Does that make sense? Okay, cool. It's color theory for engineers. It's a little bit harder. Okay, so images to gray. We can adjust contrast by, say, image equalize. So if you have a grayscale image, right, and instead of being really, really bright at one end and really, really dark and being nice and smooth, if you have a really poorly exposed image, you might just have values between, say, 100 and 200. Equalize will just take those values and stretch them out. So you get a nice, nice sort of spread on your data. You can also use the histogram stretch to pick out part of your grayscale and stretch that out because that's what you're really interested in. You can use an image histogram function, and this will just return a histogram of the grayscale values in your image. And there's also an image max val and min val, which will return the minimum value and the maximum value. So then you can kind of pick where you want to stretch. So I'll show you that using this shades of gray example, which is our friends here, the penguins. They look just the same in black and white as they do in color, which is nice. So let's say, so see, basically what I did is I moved the penguins from color to gray. If you wanted to see what they look like in regular color, I could just go. Oops. That really is the color image. They can't tell. All right, so you can take the penguins, right, and you can say, let's say I had some sort of weird task where I want to look at colors and try to figure out where the feathers are on the penguin's belly or something like that. I'm interested in this area. So I can crop out that area, and I'm just going to draw a rectangle to show it. And I can actually look at the histogram of grayscale values in the penguin, or in that little belly, right? So these render below. Oops, where'd my thing go? Where did my plot go? There it is. All right, so the blue line here is basically the penguin's belly. Is this? Let's check. All right, so red is the original, right? So I see that I have a cluster of colors between 10 and 20, and that's about it, right? And then I can, after I apply the equalize function, what I've done is I've stretched out those values. So on the left here is a number of bin counts, right? So I'm saying, how many pixels are there that have a value of 0? How many pixels are there with a value of 10? How many pixels are there with a value of 20? So what I've done is I've taken all these values and kind of stretched them out. And you can see that here. So this is the original source penguin belly. And then here is when I've stretched it out. And now I've made sort of the little gradient that you can kind of see here much more prominent. So if you wanted to say, like, look for the lighting angle, you can see, oh, well, the penguin's really bright up here, so maybe the light's coming from this way, or maybe the penguin's round and the light's like this. But it's made so much more clear by stretching out the histogram. Yeah.
So in this image, you knew what coordinates you wanted to work on because you just manually figured out I want this region.
This little
But
region.
if you had like thousands of images and you wanted to work on the same set,
The same
same
spot.
region, but for different images, how would you figure it out automatically?
I'll get to a little bit of how you find stuff here. That's like basically the next section. We'll get there a little bit, like say if you wanted to look at hues on faces or something. So where was I? So we equalized it. We showed you the histogram. If I wanted to say move the penguin, so I want to take the maximum and minimum values that I found in that belly region of the penguin, and for some reason I really just care about those in the image, and then I want to show them, I can use this max value to find it in the little penguin belly image, which is right here, and the minimum value, which is also in the little belly image. I can print those out, and I can take the original source image and stretch its histograms so that the smallest value within that range becomes 0, and the largest value in that range becomes 255. And I stretch it out so those colors become much more prominent, or those gray values become prominent. So that ends up looking like this. So I've now, everything that's below that gets set to black, everything above it gets sort of drawn out, and I've applied that to the image. So stretch is arbitrary, right? Where I say take this point, and whereas stretch means take your lowest and your highest, min and max, and just stretch it out. Yeah. A good way to sort of familiarize yourself with some of this stuff is to sit down with GIMP particularly, and look at how you modify histograms and play with them and what you can do with them. Because essentially what you're doing here is programmatically creating those tools and using them. And that will give you, using, like, say, GIMP would show you get a feel for what you're doing when you're moving histograms around and what you can find. And this is all programmatically there, but we don't have, nice graphical tools where you see the whole thing and you drag and drop and pick stuff. But this will give you a little bit of a feeling about why this is useful. And generally, you use these sorts of things to get rid of, say, noisy areas or overly light areas. Because a lot of times you'll have an image and you'll have a lighting source that's really bad and there'll be a bright spot. And you want to try to get rid of the bright spot. And you use this equalization function to get rid of those bright spots. Okay, so I think I'm going to go back to my slides, and we have one more example, and then we get to actually start finding stuff, which is where things get really meaty. So black and white. Sort of, we've already seen it a bunch. I've been going to these black and white images again and again and again. But realistically, this is the meat and potatoes of getting a lot of practical computer vision stuff done in terms of locating stuff in an image. And these are called binary images, they're just black and white. You get them using either a method called threshold, which is a really kind of like a hammer, that it just says above this value, things are white, below this value, things are black, and that is the way it is. We also have what's called image.binarize, which is a smart sort of threshold, where thresholds are set sort of locally based on what's going on in a little local region in the image. So you slide across the image like this, you slide again, and you say, well, what's going on in this area? We'll set the threshold relative to what's in there. If you don't know what you want to set your threshold at, I highly suggest just using binarize, and it'll probably get you close to the way there. So I'm going to show you an example. So
Sometimes you might be more interested in your texture rather than binary.
say that again?
Like sometimes you're interested in a particular texture and not the binary values.
Yeah. Well, we can get to sort of texture find. Yeah, you use a convolution or some sort of texture approach to get texture. This is more about finding interesting stuff that you can want to measure. So say you wanted to, and I'm just going to show you the rough example. Say you want to get this parrot, right? You want to get just the image of the parrot. You want to look at, say, the color of its feathers or the texture of its feathers, right? But you don't care about the texture of this background area. You just care about the texture of the parrot. I should just close. So to do that, right, we can start. I'll just show you what raw thresholds and raw binarization do, right? So I'm going to create the parrot image, right, which we've seen is just this green parrot. Looks like that. So I can set 3 different thresholds, right? I'm going to set 3 different thresholds to just kind of compare and contrast what they do. So I set one too low, one that's, roughly okay because it's a well-exposed image, and something that's sort of too high. And then I'm going to compare that with binarize, which is our sort of smart threshold, right? So you're going to get So here's sort of, I don't get quite enough information, right? I lose the parrot's face. I get these little lines right around here in this region. This looks okay. This is way overexposed, right? Or too much, right? We're getting not just the parrot, we're getting the background. This is not something we want. Here, maybe okay. And then, oh, sorry, this is binarized. That's pretty good. Here's setting an okay threshold, and here's setting an, not getting enough information threshold. So you can see that, okay, setting a good threshold, binarized, you're going to roughly do okay. It missed this area down here, right? This is kind of where the parrot's sitting on the perch, and it missed around here, so it's not perfect. So we want to clean this up, maybe, if we want to get the whole parrot. So we can use a couple different tools to get us a really nice segmentation of the parrot. The first one we can use are these what are called morphological operations, and they're essentially, if I have a black and white image, they move around how the black and white are distributed. So there's something called a dilation, which takes, basically, if you have, say, a single pixel, it'll put a pixel next to it, on top, on the bottom, on the right, and on the left. It'll kind of fill in a little bit. And there's erosion, right? So if you have a single pixel, it'll just blast it away. Or if you have a single pixel that's not touching anything, it'll just get rid of it. And you can apply these operations multiple times. So you can either fill things in, or you can kind of get rid of little spots. And by doing them in different orders, you can sometimes clean up a binary image. There's also sort of variants on these that are called morphological opening and closing. And generally, therefore, if you're trying to find the edge of something, they'll either open up that edge or they'll help to close it and make it more closed. There's a couple other tools you can use. There's what's called flood fill, which is just your paint bucket tool in GIMP where you say, here's a point, here's a threshold, dump some paint on it and fill it up like that. Usually use it for, like, say, white. Like you say, hey, I have these edges, but now I want to make the whole thing white, so I just want to flood fill in the center of, say, some white area. There's image.watershed, which is kind of a sophisticated algorithm that kind of auto-magically, if you have a rough blob, will figure everything out for you. This is another one of those, if you don't know what you're doing, but you think, you have a decent idea, watershed will get you probably what you want. Another good thing to think about is that sometimes if you have two exposures, right, if you take you threshold really low and then you threshold really high, you can AND those two images together or them together and get what you want, or do a logical or it's a binary image, right? So you can think about logical binary operations like AND or exclusive or NAND. And those will help you. And it's worth also noting that AND is basically a plus operation. You can take two images and say A plus B and get C, that is the AND, or A times B and get the OR. All right, so we're going to do an advanced example with our parrot again to try and get a really clean parrot blob. So I'm just going to take the regular binarization and invert it, which is okay. All right, there's our green parrot. We get something like that, but we have stuff here we don't want. We're missing stuff here that we do want. We're missing some area here around the face that we think is important, so we got to clean this up. So I can go back and revisit the hue distance, right? And I figured out the parent was 80. And I find that sort of black and white flower image, but for the parrot. I invert that and I threshold it, and that gives me another binary image that might be helpful. So that looks like this based on the parrot's color, right? Well, that's pretty good, right? It got its face, got here, which we were missing, and doesn't get a lot of image data right here. So that's useful. So we can combine those two. I can take that first one and try to get rid of some stuff by doing a flood fill. And I do the flood fill at x equals 0, so the top left, and all the way down at the bottom of height. So I do a flood fill right here to get rid of that junk. And I fill it with the color black. And then I can logically OR those two together. So here's the first one. Here's the second one. There's the flood fill result. And here's what happens when I OR the two together, which gives me something that's pretty close to the parrot blob that I want. There's still some holes here, still some black spots. I'd like to get the eye, I'd like to get that part of the neck. So I then can apply this dilate, right, that makes little tiny single pixel things bigger. And I can also erode it. We'll see what those get us. So here's the dilated parrot, right? So you can see all the little single image blobs are gone. They're either made big, or if they're a hole, right, if they're these black areas, they're made larger. So we've kind of cleaned up the speckliness by making things bigger. The erode operation, or sorry, this is the dilate operation, where we've filled everything in. We've made all those single pixels bigger. And here's the erode operation, where we've cleaned out sort of single pixels, but kind of in a more making things darker way. So neither of those are perfect. So go back up here to the code. I apply an image.watershed function to the dilated image. So I take this sort of final image and I say, this is roughly what I want. Watershed, you figure it out. And it'll get me something that's really pretty good. So there's that. There's the dilated image right there. So it's pretty good, but we still got a few holes. We got a few extra stuff over here. And I apply watershed, and it gets me this nice, smooth, pretty contour of one thing that's, you know, the entire parrot and nothing else. All right, you guys are like... we give watershed the original image, but we also can tell it a mask to use to find something, or it'll find it automatically for us. It'll guess at a mask, and it'll do a first, you know, a rough guess, a good starting point. So I'm going to go back to my slides, and oh. Yeah, well, obviously, so there's a couple different ways to do automatic segmentation. To do each one? So generally, most of the erosions, dilations, I do not have a trade-off of all of them. I mean, if you want to go back to the literature and infer, I mean, they're all at least linear in pixels, if not, you know, you try not to be n-squared in pixels. So you guys are like, why are we making things black and white? This is completely boring, not exciting, right? You're like, oh. All right. Is there any questions about kind of what was going on there either? Feel free to barrage me with questions. All right, so the reason we're making things black and white here is that we have a lot of tools built into Simple CV that actually, once you have a black and white mask image, that make it easy to start figuring stuff out. And we're going to start finding stuff now. And the way you find stuff is, right, to do this first pass where you make things black and white and kind of roughly guess where things are. So when we do finding stuff in Simple CV, you basically use find commands, and find commands return lists, what we call feature sets of features. Features have some basic properties for manipulating them that make them super easy. They will, every feature that you return from Simple CV will tell you where it's located, how big it is, what its average color is. And you can go through and apply parameters that the features have in the feature set, and you can filter on them. So if you say, find all the things in this image that are green and then filter on them by size, right? If you want to find something that's big in green versus something that's small in green, you can do that. If you want to, say, find things that are really wide and green and shaped like a square, you can do that. And there are a whole set of things you can find in Simple CV right now, and we're trying to sort of add to this base library. So there are blobs, which are essentially black and white objects that we've reapplied to the color image. So once you have a black and white image, you can take everything that's white in there and make it into one of these objects, and then calculate the mean color and its location and what its shape is. You can find lines, which are, you know, normal straight lines. You can find corners, which are where lines intersect. You can find circles, general regular round things. You can find what we call Haar features, which are more abstract things like faces, eyes, nose, heads, faces, or ears, all these sorts of things. You can find barcodes, texts, templates. Templates are example images that you've created from something else. You can find key points, which are roughly these sort of rotation invariant meaning you can rotate them different ways, kind of move them around interesting areas in an image, and you can match those. Those are a really good way of matching patterns. You can find motion between images, you can find skin tone objects, and we're trying to basically add on to this list of things that you can find in an image with one command. So basically when you say simple CV, find me blobs, find me faces, find me lines, you'll get a feature set back, and each feature set you can say draw, which means just render to the screen on the drawing layer that you can see. You can call .show, which will draw something and then pop the image up so you can see what you found. You can crop to it, so that means if I have, say, a line that's like this, I can get just the areas defined by the line, the box that defines the line. I can get its mean color, and you can get its area, basic things like that. You can take a feature set and start applying filters to it. So if you have an average color, you can start saying, start finding me things where the hue is green, or find me things where the average color is this, or where the width of the object is this. You can ask questions like, how far is this feature from some other feature? How far is this feature from the center of the image, from the top left corner of the image? These are really interesting ways of starting to frame problems when you want to solve something by looking at a picture. And the first thing that we basically use is blob finding, which are these black and white images that we kind of pull stuff out from. In Simple CV, there's a find blob command, which will basically either automatically do the black and white for you and give you a rough guess, or you can use find blobs from mask, which will allow you to give your own black and white image, and it'll return the blobs for you as a feature set. There's something called find blobs from palette, which will allow you can call a command on an image and say, give me the palette, give me the top 6 colors roughly in this image. And you can use that palette and say, well, give me all the areas in the image that are roughly this color. Like say if we go back to the flower example, where you have a pink flower on a green background, I can say, show me the palette, the top 2 colors in the palette, and now find everything that's pink from that palette. There's also find blob from watershed, which just says, I know roughly what I want, try to find it for me. So I'm going to show you guys we have 5 minutes. I don't know if we want to break early. We can get started. So here are some Christmas cookies. And so let's say we wanted to do something where we could find a particular kind of cookie. And this is kind of a toy example where you say, hey, can I find these star cookies here, these yellow star cookies out of all these other cookies? Like, there's something I have a description for that I can see that I want to programmatically find. So we can start looking into how we get cookies. All right, so I'm going to take our original cookie image and say I wanted to find that yellow sugar cookie up in the corner. So I can I can say on the image of the sugar cookie that I just loaded to find the blobs. So I give it a threshold value, right? So this basically applies that threshold operation that we had, which is 128, and I'm going to say min size, so 200. So that means, anything that's bigger than roughly, it can't be a tiny little 1 pixel thing. It has to be something that's got some size to it. And draw them all with an outline, draw them all filled in and draw them red and show me what you found. So after this first call, we see that we found something like this. So these are everything labeled red here is a blob that we found. Yeah.
On the size, since it's like an irregular shaped thing, what does size mean?
Okay, so say if you had the black and white image, right, the binary image, the size would be the number. So if nothing's touching it, right, if you have just, say, a white square on a black background, it would be the number of pixels that are white. So here's what happens after we just say, find blobs with a raw threshold, right? So each of these things here is a blob. It's a blob object that I can actually go through and play with. So I can say, over this list of blobs, I can call the command that says area, right? Let me show you what that looks like a little bit. So here, for every red thing that's labeled red in the image, I can actually see how big it is in terms of pixels, right? So I can then filter all this stuff on that area. So I can say, hey, image, give me the mean area. Take all those values, give me the mean. This is just using the numpy mean command, which you just say, NP is the normal abbreviation for numpy. You say, numpy, give me the mean of this list of things I just gave you. And also give me the standard deviation of that mean. And then I say, give me the cookies that aren't, there's that big, huge red thing right here, right? So we don't want this. We want to get rid of that. That's too big. It's obviously not a cookie. Or it's obviously a bunch of cookies glommed onto each other. So I say, hey, blobs, filter out all the blobs where the area is less than the average area times 2.5 standard deviations. And then I can take that same list, I can save it as a new list of blobs, and I can draw them again, and this time draw it all as green. So let's just see what that looks like. So here's before, right? We have that big giant blob, but we don't want that. We said only take the ones that are below, that aren't the giant blobs. And here we can say, okay, well, we got rid of that giant red blob. We now have just these small regular cookies right here. All right. So now that we've got the small cookies, right? Let's see if we can find the ones that are just yellow. Right? So I can say, take the little cookies, take this new list that I've created, and I can say, feature set, sort these on color distance. How far is the average color of each of these single cookies from the color yellow, right? So I'm saying if you're really close, you're going to get a small value. So, and this will automatically sort things for us, right? So I say cookies sort on the color distance and how far the color is from yellow. Now give me the first 4 cookies, the ones with the small, or that are closest to yellow, and draw those as yellow and show me what you got. And so here's our source image. There was the original set of things we got. There's the ones after we got rid of the big one. Now here are the 4 that are closest to yellow. The first 4 that are closest to yellow. Not bad, right? So we've eliminated all these other pixels as being our potential, like, nice yellow cookie in the corner. So then I can say, hey, cookies, I still want to find the one that is in that top right corner. So tell me, of the list that remains, of those 4, tell me the distance they are from this point, which is the width, so all the way over on the right, and y, so no y, so all the way top left corner. Sort them by how far they are, or give me the distance from that point. Now sort them, and this is where we're using the np-where function, so it says, take the list of distances here and sort them, or show me where in that list it's minimal. So say if you have 4 cookies, the 4 yellow cookies, you say, well, how far are they away? And you calculate how far away they are. And you say, I want to say this is the closest one to the corner. So I get that location. I'm going to crop that cookie out, just get an image of it by itself. And then I'm going to draw it as hot pink. So we're going to go down here. Oops. And here is our selected top right yellow cookie. And here is the actual image of where it is. So you can see how you can kind of build up a grammar of how to search through an image to find what you want, right? At least, I mean, this is one aspect of computer vision. Any questions about that? Yeah.
So why is it that it couldn't distinguish the cookies in kind of like the middle part on the bottom? It's got this big blob instead of 10 cookies. Is it because they're touching a little bit?
Yeah, it's because they're touching, and if you use like a raw threshold, right? There's if we go back to this image, you can see that there's like this little bit of like this brightness, this specularity, right where the camera flash was. Specularity is usually not your friend. So it's blowing out the values in that area a little bit. So if you say, give me everything that's brighter than the gray background of the cookie sheet, well, the gray background right here is actually brighter than it is over here. So when you kind of try to set a raw threshold, you don't get all of that. Does that make sense? Well, so you could use a hue of the background of the grayness here. Since the cookies are all different colors, right, you can't use their color. Like you can't say, give me everything that's green because they're not all green. But you can say, give me everything that's not the background. This is kind of complex. Anyone have any questions? Does that make sense?
Here you're making an assumption. You already have some knowledge about things.
Yes.
You know that where people are looking for. How would, I imagine the problem was the ultimate difficulty to just accepting any random picture that might look similar to this, but you don't know exactly what it's focused on.
I think you're exactly right. If you, in completely unstructured data where you know nothing, it becomes very, very hard. Now, if you know that if you're putting a camera in your kitchen, right, and you can make part of what motivates doing stuff correct, or how you kind of motivate doing things correctly, is think about all the assumptions that you're going to make when you want to look for something. There's really no good way to sit down and say, well, in the universe of all possible images, because there's an infinite number of images, that it's always going to be like this. So you kind of have to constrain things and say, well, the cookies are always going to be on a gray cookie sheet. How can I use that to my advantage to figure out what I want to do?
Even if you set up an example of this, where the yellow star-shaped cookies are in the bottom, for instance, not on the top,
Mm-hmm.
without making an assumption where the cookies are, because you extracted this top right cookie
Mm-hmm.
based on the distance from the top left corner.
Well, yeah, so that's an arbitrary example, right, where I say I want to find that particular one, just to show that I can search by distance from something. But if I wanted to say, just give me things that are yellowish, that was the step before that, right, where it's saying, show me which ones are yellow. So if I was only looking for yellow cookies, well, now I know. And then I can kind of infer that, hey, tell me how far they are away from the center, or tell me how far they are away from the top, or however you want to slice that. Because this is all application specific, right? But we give you the tools to get there. All right, so are we due for like a few minutes here? Do you guys need to? Okay, is it making sense? Feel free to come and bug me with questions. So I guess we have 10 minutes. It's in Simple CV examples and presentations, and it's all the text, so you can regenerate everything, but there's also the PDF of the talk. There's a zip file of the IPython notebook. They're pretty big, so I zip it. There's a couple little example Python files in there too. All the images, right, that we're using, they're all in there. So you can basically recreate what's on, once you go home, once you set up Simple CV on your host operating system and you want to go through the tutorial again, you can, and this will basically replicate it all over again. So you can kind of go back home, review, and get all this stuff. And I'm hoping that as things change, as I get more time to write more slides, that effectively we will keep this up to date-ish, because I try to do this once every couple months. So, new stuff, cool stuff, whatever, we'll hopefully get in this sort of examples folder. Yeah.
So get more GT functions.
Uh-huh.
Could you show an example of how it works? So when I do color.red, I get a 2 plus 2 bypass. So say when I try and produce a color red, I just get hue from RGB. I can't find the combination of parameters.
I have to check at that function, because that was really the RGB mapping to, so you do an RGB to HSV mapping and then you return the Q, and I think it may not, my guess is that there's actually some, there might be a bug. If it's not returning the right value from RGB, then and it's not going to, and twiddling the channels doesn't work, then it might actually be a problem. Okay.
So RGB to HSV is a one-to-one mapping?
No, it is not a linear mapping at all, I don't think. Color space remapping is generally, it's solved, like it's generally, like, it might be a linear mapping. I don't know, I'd have to look it up.
But it's a one-to-one mapping. It may not be a linear.
I don't even know about that.
Can you show the command line?
Oh, command line, certainly. So command line for IPython is going to be, I don't want to restart it here, but in the presentations directory, here I'm going to make a bunch of spaces so you can see it. Simple CV, notebook, -pylab equals inline. Pylab inline tells Python, or tells the notebook, that when it loads matplotlib, that the matplotlib figures should be in the body of the notebook and not pop up in separate windows. So that keeps everything in the notebook, which is nice. But it's not very, we're still having problems where we want picture, notebook, picture, notebook, picture. It's not quite there yet. Okay, so you guys feel about ready for me to keep pressing on here? You feeling it's getting more interesting and useful now that we've gotten past some of the boring, kind of crazy stuff? Getting there. Getting closer? All right, we'll hopefully get there pretty quick.
How did you get it where you had the video of you and it had just your outline and all the edges and things? It was like a real-time video?
Oh.
Where the beginning you showed?
Oh, so basically all I'm doing there, right, is when you have a camera, right, you can actually create a camera object. And if you say camera.getImage and you do it in a loop, in a while loop or whatever sort of loop you have, it'll just go as quickly as it can and save it and put it out. So you can take, whatever image processing you're doing and put it in a loop and see it as video. Now it may not.
Like to take a stored video and transform it to an edge video.
Yeah, you can do that using the virtual camera class. And you can treat that as a camera and do the same thing. Okay, so we've found all sorts of cookies. Right, that's where we left things. We went through here and we found this yellow cookie up in the corner just as a toy example of how we talk about, how you think about these problems, like at least finding problems, right? The Blob class actually has a lot of other just super cool stuff in it that makes your life way easier. There's a min-rect, which is the minimum bounding rectangle. So if it's basically the closest square thing that'll fit your thing. There's a contour, right? Which is the contour is the outer edge of your blob in terms of XY points. And that's really helpful if, like, say you had a hand blob or something, and a common task is you want to find the holes where the fingers are. You can iterate over that list of XY points and kind of figure out where things are. There's also something called it's formally called the convex hull. We'll just call it the hull. And the best description of that, right, is if you had a bunch of XY, so if each of your XY points on your edge is a nail in a board, right? And you take a rubber band and you snap it around the board, the rubber band forms the convex hull of the nails in the board. Does that make sense? We also have there's some features for like the holes inside of a contour, because what you can have, right, is you can have, say you had a nice single color background and then you had a donut, and the donut had a donut hole in it, and the donut hole was actually another donut, and so on and so forth. So you can have outer contours, little islands inside, or little lakes inside the island with islands inside that lake, with lakes inside of them. So you can kind of recursively go down this pipeline of stuff inside blobs if you want. Blobs, you can draw the rectangle, which is just the outside. You can draw the minimum bounding rectangle. You can draw just the outline. You can draw just the holes. You can draw the convex hull. You can draw the edges. You can draw all sorts of stuff. So I'm going to do an example of just that. So if you go to your notebook, and if I don't scroll these things up, I know this is kind of jerky scrolling. Yell at me. Just say, hey, if you can't see. So here, I have this image, and let me show it to you. Image.show, right? I just have this image I pulled down on the web. It's probably somebody's hand on a scanner, right? But it's nice because it's got a nice black background, so I can find stuff easy. And this is just an example of what you can do with blobs. So I say, hey, blobs, find me, just find blobs, whatever. You can guess at it. This should be pretty easy. That are bigger than 200, so get rid of any little tiny outlines and return them. So this is a list. Actually, we'll see if there's anything else in here. Print blobs. Oops. Nope, there is only one blob, so I will take the 0th blob. And then I will draw the hull, which is, again, the convex hull. It's that nail rubber band thing that we talked about. I'll draw it. I'll draw the rectangle around it, the minimum bounding rectangle, the holes inside of it, and I'll draw all those and show them to you. So we can see here. Here's the outline of our blob, which is the red, right? All the way around. You can see the holes here. They're outlined in yellow. So these were little areas where the segmentation kind of had something inside. Here, this outer magenta, and it's covered up by some of the other features, right? But this is the convex hull around the hand, so we don't get any of this finger stuff. We don't get this spot between the thumb. Then we have the minimum bounding rectangle, which is just the rotated rectangle that is the smallest rectangle possible around it. And then finally this nice XY rectangle that we all know and love. So you get all of those things inside the blob, and those are all available as something you can draw or as something you can get a bunch of points with and play with and figure something out from. Question?
Now, on the previous slide, you talked about that draw outline method, and then in your example here, you use draw, not draw outline. Are they the same?
I think draw will draw both the, I have to check on this. Draw will draw both the, like if you say draw with -1, which means filled in, right? It'll draw everything that is not the holes, so it'll draw the interior and the holes and everything else. So draw outline will not draw the holes. It'll just draw the external edge. So along with this, we're going to go back over here to the slides. Oops. Along with this example, you can also take any of these things that you would want to draw and get them as images. And this is sometimes, there's applications where this can be extremely useful, where I just want to look at this one thing inside the blob. Hey, I just really care about the outline of it. I just care about the mask of it. So each of the blobs has basically a method that will allow you to get the image, which is just the area, just the pixels inside of the blob. It'll let you get the hull image, which is just the pixels inside of the hull. It'll let you get a blob mask, which is you take the rectangle, the square rectangle, and you return basically the black and white image that you used to create it. Same thing with the hull. You can also use what are called these, I call them full masked images. So I return an image that is the same size as the original with everything in place. So like if you have a little tiny circle blob in the corner and I say get full masked image, it'll return a black image where just a little white portion is in the image. And this can be useful if you want to put stuff together in a certain way. So I'll show you guys an example of that. So I'm just, this is kind of this can be kind of fun. I have there's a side-by-side method in Simple CV where you add another image to another image. It's sometimes useful for doing like before and after or comparison. So I'm just using that here to generate some of these images. So what I'm going to do is I'm going to take this, this image here of these kangaroos, and there's an albino kangaroo, which means he's nice and easy to segment. And I'm going to apply each of these methods. So first I'm going to start with the blob, just raw blob relative actions. So here you can see, here is the blob itself as the image. So we've gotten rid of everything that's in the background, all of this stuff. We're just returning what we think is the blob. This is just the hull, right? Here is the mask. Here's the hull mask, right? So the nails in a board mask. And here's the edges too. So because sometimes the edge image is more important than the blob itself. And then here's an example of it being used in terms of the whole image context. So here is the masked blob, but it's the same size as the original image. Here's the hull, the mask itself. So if you wanted to say, use this mask to flood fill the albino kangaroo green or something, you could totally do that. Here's the outline, and here's the convex hull outline. Okay. Actually, somebody was asking me about this a little bit more. There's inside of blobs, there's also some notions about shape, right? Because shape's really important when you want to segment things. We were looking for cookies that were yellow and at the top of the screen, but what if we said, no, we really are interested in stars? You know, you have these Lucky Charms, and I want to, you're eating cereal, I have these Lucky Charms, I want to find just the stars in the Lucky Charms, and you have some notion of shape about what you want to find. So you have stuff like the area of the blob, that kind of defines its shape, the perimeter, right? The ratio of a perimeter to area is kind of interesting. It's useful for figuring stuff out. The angle, which is the angle of the minimum bounding rectangle. The centroid, which is different than the center of the blob. That's like if you had the letter C, right? Its centroid is still in the center, right? Or roughly in the center. Right, it's shifted over because of the mass. There's blob rotate functions. There also, for blobs, there are circle distance and is circle, is rectangle, and is square. So if you're looking for something that falls into this basic language of round, square, rectangle, you can ask that question of the feature set and say, show me stuff that's round by setting a tolerance. There's finally a blob.match, which is a shape match parameter, which we use something that's called a hue moment. If you guys are familiar with physics, right, you know about the moment of inertia. So if you take a tire and you spin it, you put it on an axle and you spin it, spin's really easy, right? But if you take something that's kind of weirdly shaped and you try to spin it, you have some inertia. It becomes harder to spin. So you kind of take that analogy in images and you use that to figure out shape. And how things spin is basically how if they spin the same, they're probably kind of similar. So I have a little example here going back to the cookies, right, of how we go and we look for the star cookies. Oops. So let's go back. Oh, sorry. Okay, so we load up our cookie image, and we're just going to find blobs from Watershed, because that's usually pretty good. It usually works. And by default, all blobs are sorted by area, with the last thing in your list being the biggest thing. So we're just going to take, we're going to get rid of everything but the last 4. We're going to do a simpler sort than getting rid of what we did before. So we're going to draw that with a width of 2 and a color of red. So that's going to look like this. We got all these, right? Now what I'm going to do is I am going to say, what is my roundest cookie? So I just say 4B in blobs. So I'm iterating. This is a Python list comprehension. Take each blob and say circle distance. And all this asks is, it returns a number that says how far is each of these away from being a circle. There's also is circle, where there's a tolerance. And if it's something that is circular or something is rectangle, something is rectangular, it'll return true or false based on whatever the default tolerance values, or you can set them. So what I can do is I can take this list of how round each of the blobs are, And I use the NP where, the numpy where. So tell me where the roundness is the lowest, or sorry, where the difference from being round is the greatest. And then I'll draw that as blue. So if we go past here. So this is of the cookies we have, right, this is the closest to being round. I can take a test blob. So let's say from those cookies, right, I have a template that I want to match. So in this case, I'm going to pick the second cookie from the last and color it with cyan. Right, so that would be, so do I need to rerun this? Oh, here. So you see this horse-shaped cookie right here? This is, say, well, how do I find the next one that looks like this in terms of shape? So the way you do that is that you go and you say, okay, so I'm going to take this out of my list of blobs, the one that I'm using as my test. Take that list out, and then I say, for each blob, I do this list comprehension again, and I say, for each blob, match it against the one I'm testing. And this match number will return a number that is a guess at how far away the shape is from the input shape. So what does that mean? That means the lower the shape match, the better it is. Because if they're the same thing, their distance from each other would be 0. And if they're farther away, it's going to be a bigger number. So the lower the number is on that sort of match value, the better they are. For this, it's rotation invariant. It's not the most robust metric, but it is rotation invariant.
What's it based on?
It's based on the hue moment. So a hue moment is just like a rotation invariant moment of inertia, basically. I'm pretty sure, but I have to check on that. I'm pretty sure it's scale invariant. If it's flipped, that is not a rotation, so wait. If it's flipped as in it's rotated?
It's flipped, it should have the same moment of inertia.
Yeah, I think it should match. So we do that. We say where is match the minimal and return that value. And so I'm going to draw that as hot pink, right? So we go in here. Here's this guy, and this is our hot pink color, right? So this is right here, which, it's a pretty good approximation. It's missing a little bit up here, so. And then we can set that. I'm going to set that to infinite, just make it huge, and then find the next minimal value. So what's the second most horse-like looking cookie that we have compared to after the first one? And draw that yellow, and it turns out it's this pig-like thing based on the metric that we've picked. So you can see kind of how you build up a grammar of matching templates, color, flavor, all these things to be able to break images down into their subcomponents. All right, so that's question.
Sorry, I know that it's probably not something you can directly address, but there's another extremely horse-like thing that's in the image that it didn't pick.
Mm-hmm.
That it's just like, it looks almost exactly like the original horse, and it's just a very slight variation on it. It doesn't get picked.
Because it's only picking the best pick, one pick.
This guy. This was the first one, and why the metric doesn't match, I am not completely sure.
It's just extremely similar to the cyan that was originally chosen. It has way more looking than the yellow shape. Like, somehow it missed it.
This is true. So we could look at the metric and say like, what are the values and what does it come up with? Because you're going to pass it through. It's going to, these aren't always fully intuitive that they're going to match, right? Because
Yeah, there's probably something that I see because I'm using it, not actually.
It could be that, this just generally has a smaller match value across something else. And it probably might be in the top 4 or something. Maybe. Like, we could see. Another question? Okay. So that's blobs in a nutshell. We can go back and do some of the other find methods, right? So the next probably most common thing you're going to want to find are lines. So if you're, this is basically an extension of the image edges. So a common one of the more common things you're going to see in computer vision is like something like a canny edge detector, right? And this will just find areas where color changes quickly and you see edges. So basically you take that edge image and you feed it into an algorithm and you can guess where the straight lines are. This is only applied to straight lines, not towards like curvy arbitrary lines. And you can get at this using the find lines method, and it will return a feature set of lines that are, and you can get their angle, how long they are, their location, this sorts of thing, and you can filter on that. You can also find the line intersections. So if you want to see where some line intersects some other line, you can extend them to the edges. If you have a small value and you want to make it bigger, the sort of general things that you would want to do line manipulation. So I'll show you an example of that. And this is actually kind of a cool technique because you use it a lot for, vanishing point. If you have like the classic sort of painting thing where you have a vanishing point, you want to figure out what sort of the perspective looks like on an image, or finding lines becomes useful if you're doing like sort of wall following or tracking if you're building a mobile robot. So these things can be kind of cool to do. So I got this image of basically a hotel hallway, which I'm sure a lot of you are familiar with this week. You see these long hallways. They have nice lines going here, nice vertical edges, nice horizontal edges, and then some sort of lines that sort of define the vanishing point. So first off, I can take that image, right, and I can take the edges off of it. So what would the computer see if I just say, take this edge detector and apply it to the image? And you get something, right, that looks like that.
Will your software find vanishing points?
Not yet. I mean, that'd be something nice to figure out. I mean, because the other thing is you don't always know if there is a very easy to find vanishing point. You could easily write something, though, that would, right? So then I can say find lines, right? So I'm going to find the lines here, and I'll just show you what they look like raw after you call the draw command. So this is basically all of the lines over a certain length threshold that we've found in the image. So we've now broken it down into just a problem of lines, and I can use the filter command just like I did on blobs, right? So I can say, show me only lines that are longer than 50. So those are the ones I just showed you. Now take the lines where the angle of the line is something that's vertical. So the angle, the absolute value of the angle is greater than 80. Give me lines that are horizontal. That is, the absolute value of the angle is less than 10. And color those different colors, right? And then show me the results. So you can get something like this, right? So basically all the green lines now, right, are probably lines that are going to start defining our vanishing point. Our vertical lines are going to tell us something, right, about where the doors start and end. Horizontal lines are going to tell us where the floor is and where the ceilings are. So you can start breaking down a problem like that if you want to kind of figure out where you are in this hallway. And lines, have all the same sort of properties where it's a list of features and you can sort on the features, and you can say, if I wanted to take line sub -1 and crop it out and just show me where that is on the image and then do some processing on that, you totally can. See, so that's a vertical line, obviously. All right. So lines. Similarly, circles, and these are for perfectly round circles, not for ellipses or anything like that. You can find circles in an image and use that to process something. And generally all the same filtering characteristics apply, right? So you can filter on the size, the area of the circle, the width, the height, the average color, all of those things. Find circles is a little persnickety that you're going to have to set a couple thresholds usually for it to work. And if you set the thresholds too high, it can not work so well. So I have an example of that. So here's this crazy guy, and he's got this clock, right? So I would want to go, let's say I wanted to read the dial on the hands on the clock, right? The world's best, or the world's worst sort of time management system. So I can just say, on this image, it's not possible to find the edges straight off the raw image. So what I do, right, is I take the image and I binarize it. So I'll show you what that looks like. So here's a little bit better representation. And then I call the find circle method, and I set a threshold. And this threshold is just a number. If you look at the documentation, it'll tell you, roughly what we use as a good starting point, and what going up and lowering the threshold does, what going up on the threshold does. So you find a list of circles, and those end up looking like that, right? And circle detection is a little odd that it'll find a lot of sort of false positives where there's a little bit like a corner piece of a circle but not the entire thing. So it's really any sort of round edges. But the largest circle, if I sort it on area, so I just do circles.sort area, the last circle, and I crop it and I can save it. Looks like that. And there's the clock face. And if you wanted to then say use find lines to find where the dials were, you could probably figure it out. And you then find the intersection point of the dial or of the hands with the outer bezel of the clock and use that to tell the time. You probably could pretty easily. Mm-hmm.
So when you try to match a shape and it produces a match, does it also tell you like how confident it is that it is exactly?
Well, so your distance value is a notion of your confidence, right? Because if it were 0, it'd be a perfect match. And the farther it gets away from that, the less of a match it is. Okay. So we've gotten lines, circles, blobs. We've gotten basically a good chunk of your sort of primitives, right? So the next sort of stopping point here, or the next sort of image point, is when you have example images that you then want to use to find stuff. And we use what's called a find template. And templates are basically chunks of images that you want to use to find something else. So if you have an example of something. Generally, templates for this sort of application, they're not really robust to rotation. They're not really robust to changing illumination that much. But if you are going to look for something over and over and over again, and you have pretty controlled settings, they're really good for finding things. And if you want to, you can kind of hack it, right? So if you have a template and you rotate it a little bit, you can build in sort of some rotation and variance. Also, if you have lighting problems, but you still want to try to use a template match, a template works really well if you give it what we call the gradient image or the Sobel image, which just tells you, here's an approximation of the edges that are in the image. So here I'm going to do an example of looking at coins to do template matching. So I have this coin image, right? Let's actually show the raw image. So this is what it looks like. This was just some of my pocket change at the office, some quarters, some pennies, a couple nickels, a dime, these sorts of things, right? So what I do first is I'm going to build my own template sort of programmatically. So I say, take the image, threshold it, invert that, create a mask, and then I use the mask to find some blobs. And I show myself where the blobs are. Right, so here, 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 here. So it finds all the coins. So I'm going to tell it that, say, the fifth blob from the end is something I want to share. So I'm going to crop it out and save that as a template. So let's see what my template looks like. So my template is this quarter. So I can take that cropped image, I can take that source image, and then say, use that as a template to find other quarters. So I basically take the find template method. I say image find template. I pass it the quarter image that I just made. I set the threshold to something, and the threshold is basically what you're going to tweak to get the performance that you want on certain tasks. So once I call that method, I'm going to get a list of matches for that object, and I'm going to color them as red. So let's see how that looks.
I'm sorry, say that again. So you set the threshold because you, for performance reasons?
Well, for performance reasons, not in terms of like algorithmic performance, but in terms of, and if you look at the documentation, I kind of say what the threshold means. But basically, you know, if you lower the threshold for most things, you're going to let more things slide through. And if you bring the threshold up, you're going to let less things be classified as what you want. So I kind of set it at a level that would show me all the other, get most of the other quarters in the image, right? So at that threshold, it gets the first three, but it misses this one.
How is it, I mean, what is it doing to compare to before you had few moments? Is it the same kind of thing?
Well, so what's going on? What goes on underneath the covers here is that, so we'll start with sort of the naive thing. So say it was binary, right? It was just a black and white image and there were some scrolly things. If you took your template, right, your black and white template, and took your image and started at the top pixel and said, take this image, subtract the difference between the other image, and sum it all up and return the value, right? And if you move that template along, right, move it along the image, scan the whole image like that, and then return the value, you know, where it was minimal would probably be your match, right? So it doesn't do exactly that. It does it does a convolution essentially. But it's that same sort of process where you're sliding your template along and you're finding where the best match is. So you can repeat this, and I repeat this with the penny, right? So you can see it doesn't always work perfectly because it's getting this kind of unshape, and you would think they would only get pennies with heads versus tail side. But generally, as a workhorse algorithm, it's pretty good to get simple stuff, and it's quick to do, right? Because you can just find a template really quick.
Why did the algorithm catch these points?
Well, so if I had to guess, my intuition would be, so if I think this one's our template, right? This one has, lots of space where, lots of difference between the dark and light regions. This one is not as well as exposed. You see it's less contrasty. So that would be my guess as to why it's not finding that quarter. And that's sort of the intuition thing. Okay, so let's go back to, this one's going to be fun. All right, so we found templates, we found quarters. You guys are now more than ready to go home, dump your change drawers out, and write algorithms that will count it all up, right? And you'll make money like Coinstar and be rich. And all right, so another thing, and I think if people, we're intentionally not doing a lot of live video things here, just because you guys can't, because you're working in the VMs. But a thing you often want to do with computer vision is you want to find things moving, because usually if you have a camera running all day, most of the time it's not pointed at something interesting, and you want to catch the 5 minutes a day that the squirrel comes up to the squirrel feeder, or your cat is at its cat bowl, or the, whatever periodic thing that you want to catch. When things move, it's interesting. When things don't move, there's probably not a whole lot of stuff going on. So we have a basic method in Simple CV called find motion. And find motion is a little bit different than the other find methods in that motion is a temporal thing, right? So you have to pass it images in series, but all you have to do is pass it the last frame. So if you have a video, right, you say you're capturing frames successively, and you just say find it from the last image. So you say, here's my current image, here's the previous image, find the motion in the image. And we use an algorithm called optical flow for most of this. There are 2 or 3 different flavors of this algorithm. Some are slower than others, some are more robust than others. This is something you mess with and monkey with, and you tailor it to your application, and you see what they do. There's also another parameter to tweak called window, which is the sample window size. So how big you want to do it, how small you want to do it, or how big a window you want to look in for motion. If you have lots of big motion, you have to look in big windows. If you have little tiny motion, you should look in little windows is generally what you want. Likewise, the image should have edges, right? Because motion, you can't see motion. If you take a camera and go like this against a white wall, you really have a hard time telling it's moving because you have no frame of reference to see motion. So you need to be able to see edges to detect motion. So if you have a really boring image, you may not see anything move. Oh, and by default, everything is rendered to a unit length just to make things more obvious and kind of usable. So I'm going to show you guys quickly, there's a little example in the notebook. So here's my desk. I took 2 photos in succession. I just moved my camera around, right? And they're kind of big, so I scale them down. Scale them to half size, show the first one, scale the second one down. So here you can see I kind of move the camera to the right because everything shifts to the left. If you look at Chicken Man here, he moves to the left. And I can say find motion given the previous image, use this particular method, and give me a window of 27 and show me what the motion looks like. So you get something that looks like this. Each of these little tails kind of points in the direction of the movement. And just like our feature sets before, I can say filter it on the magnitude of the motion. So show me only areas where there were a lot of motion, show me a lot less. Not really relevant when you have the camera moving and everything else sitting still. So I'm going to do a live example here because that actually shows what's going on. So Python, actually let's look at it real quick, but less motion example. So here it is, really short, really sweet. Just import simple CV, create a camera, create a display. I'm scaling the image just to make things render quicker. So I create a scaling value. And basically I create a while loop, get an image, do the find motion command, and then I draw the motion and I save it to a display. So I'm going to Python motion example. My camera should fire up here. So you can see where the camera, so one of the things that's going to happen here is my camera's got a little bit of auto exposure, so that's going to make things pulse a little bit, but generally if you move around, this is totally trippy view, right? So you could basically, now I can see that these lines, right, they have magnitude, so where things are, if I do things really boring, well, the magnitude's all screwed because there's no motion, but you can look at the direction of those vectors and the values of those vectors and start being able to figure things out, right? I'm not going to cover it today, but there's also a couple tracking libraries we have built in that do, look at images temporally and find that they kind of goes along with this, where you look at images through time, you look at the difference of, say, color or texture, and you can track something, and they add on basically some stuff that helps filter out the tracking, and then you can treat the track, the temporal series of positions in XY space, as a feature set itself, and you can start filtering on that. That tends to get a little bit more advanced, so we're trying to stick to the basics today. Yeah.
Would it be possible to detect movement that you actually cannot see, like some kind of fault or some kind of solution that moves, but the human eye cannot see, but the machine can see? Would it be possible to have any example?
Well, so there was did you see there was a suite? I'm going to get off a tangent here, so I have to keep it really short. There was a group at MIT, right, who was doing, they've temporarily filtered stuff like babies sleeping, right? And you could see the pulse on the baby's face. So you can actually amplify motion. This is not something we have support for, but you definitely can look at a set of temporal images and do something like that, right? And the reason when it holds still that everything goes a little crazy is that I'm scaling to unit length, so I take the longest thing. So when you don't have any motion, and it kind of makes things pulse and go weird. like an analog camera. Generally, so that's kind of old school, right? You have to have some sort of something called a frame grabber, right? That basically does that. And then if you can treat it as a USB device or however you want to get to there. I mean, yeah. I mean, so the really hacky solution, right, is if you have like, say you have a really old TV camera, right? Buy a web camera, point the camera at the TV, and the worst capture method ever. All right, so we did this. Here's our motion example. So here's another really common one that we helped to fix because it wasn't in OpenCV, it wasn't anywhere except in these existing libraries. And these are probably the two biggest optional libraries you're going to want to download. So the first one is finding barcodes. Everyone loves these QR codes where you snap a picture of your phone, you read the barcode, you get information. So we basically have utilities in there that allow you to read QR codes. And it's just like everything else. Find this. So find barcodes. It'll return a barcode feature which has the data in the QR code or the barcode, the position of where the barcode was found, that sort of thing. We actually have support for two different libraries because there's two different competing libraries to do this. There is libzebra-crossing, or it's called zxing. And there's, that one's generally, I think, better, and there's also zlib. We have hooks in them for both. So if you have, I think zxing is better for generally QR codes, if that's where you're going. I think zlib is better for odd barcodes. So if you have like, we in business stuff have these different formats that we have to use, and zlib actually tends to have more support for weird barcode formats, but it's not as robust to rotation and stuff. So be aware, it may not always find your barcode. You may want to rotate your image to straighten things out or that sort of thing. Along those lines, we also support a read text function, and it just returns the string that it found, and that's using an OCR library called Tesseract. Generally, you're taking, if you use OCR and you're returning a string, there's a bunch of stuff in there that has to do with your formatting. So you'll get lots of new line characters and tabs, and just, it's not perfect. So it'll be a little choppy, but you can usually get chunks of text out of there if you're good at string parsing. So here's I'm going to show you guys an example of doing QR codes. So here's just one I auto-generated. Open it up, QR image, find QR code, I can show it, and I can print the data super quick, like so. I just use draw text, and I take the data from the QR code and put it on the image. So it's a little not too contrasty, but it says, hello, simple CV tutorial, and that's what's in the QR code. So if you have QR codes you want to read that are coming in, say, from somebody posting from a cell phone, we can do that really quick. I also have here an image of my business card, right, that has my address, lots of different fonts and stuff. Yes?
How robust were lib crossing against rotation and distortion? When I played with it a year ago, I found it wasn't terribly convincing. Up close, personal, straight on, it was good, but with any distance, it got very rotated.
Yeah, there are certainly robustness issues. Like, you know, you'd like to think that every time you have a barcode, no matter what your angle you come at it, like it'll work perfectly. And the truth is, the barcode libraries aren't always. I mean, these are libraries that I don't have any control over, so they're not always as robust as I'd like. So you can do stuff like. The smart money, if you have a barcode or a QR code, right, is to find the lines in the image, right? And you should have a set of orthogonal lines that should be vertical and be horizontal, right? And they're all going to point to a rotation. You know, if you can infer the rotation that you're going to need to make to get things straight, and then rotate it, and then actually be able to read the barcode. That would be the quick way of trying to solve that problem. So here would be my card, right? So let's see if I can try and read it and get all my information on it. So you can just call the read text function. Why? So let's take a look at that string. So you can see that the string, this is the string that comes out of the OCR library. So it's trying to find stuff. It kind of screws up on all the imagery at the top, but when you get down to the where the lines are, where the real text is, you get some, pretty high signal. Like, okay, address is correct, phone number is correct, email address is correct, all that stuff it got. So you're gonna have to kind of dig through all the text that it finds sort of accidentally, but you'll get the text that you want. Tesseract, there's a Python, it is PyTesseract, I think. I don't doubt it for a second. No, I would love to see them actually. Okay, so we got text, we got QR code. I know people had questions about that. So the next sort of thing, we'll do more fun stuff here, right? So the next thing that you're going to want to talk about is I talked about these Haar features, right? The things that make faces, that make that you can use to find faces, that you can use to find more abstract ideas in an image, right? So face finding. If you read the history of it, it's really kind of cool, like how we actually taught computers to robustly see faces. And I'm not going to go into the long history of it, but there's, the very earliest machine learning algorithms that really worked kind of were face finding. And it was this huge challenge. There was probably 10 years and millions of dollars that went into figuring out how you take a bunch of images and you start figuring out faces, but now it actually works really well. So this is all, you can get at this really sweet research by just calling image.find Haar features. And Haar refers to one of the algorithms that kind of live inside doing face finding. There you can see what kind of features you can list or have by calling list Haar features. And these, we package these up into Simple CV so they're easy to find. And you just
Compare two images and see if they're the same person?
No. So doing biometrics where you actually look at the difference between two people is a different problem than just saying a face is there. These are different classes of problems. And the other one is something I'd like to start solving soon, and you use a whole different set of tools to do that. But the first step there is to be able to find a face. So this is the start of that. So we're going to do something a little bit cool. Where we swap faces, right? So I'm going to write this little algorithm called swap. And I'm going to take in two images and two face objects. And basically what I'm going to do is I'm going to take each face, and faces are just features like we've seen for features for blobs, features for lines, features for circles, same thing. So I can call crop, which will return an image. I can call resize on that image so I can scale them. So basically I trade the cropped resizes of images. And then I use this blit function, right, that we were using on Richard Nixon to move his face around. And I can blit one face onto the other and another face. So then I actually go and get the faces. I load in two images. I'll show you what they look like. I then say find Haar features, and in this case I say face.xml. The Haar features are in XML files, basically, that defines what's going to go on inside the Haar. And I call swap, and I save the results. So here's what this looks like. All right, so here's good old Richard Nixon. Here's another leader of the free world. Here's Captain Picard, right? So we can call find faces on them, and it will just return a box where the face is, roughly correctly centered. Here's Captain Picard. And then I can call my swap method on them and blit them back in. And it actually works pretty well. And this is generally fast enough that if I wanted to run it on a camera, I could do it, in real time. Might want to scale it down to half resolution, but that's about it. So we're going to do another one. So faces are just a start. You can actually, I don't think I have the entire list here. But you can do eyes, nose, mouth, ears, I think, eyes with glasses, upper torso, profiles of faces. Those are the ones that we have baked in right now. There might be a couple that I'm missing. I think you can do left and right eyes versus just eyes. Along those lines, it's not 100% perfected, but you can move stuff around to a certain color space, and people have done research on roughly what colors constitute skin tone, even though it's really actually pretty hard to designate skin tone versus anything else, but you can roughly say, well, it's in the spectrum of this space. So we have that, and you can also use that to figure some stuff out.
Is that racially invariant?
Supposedly, based off the paper, it is. I actually have an issue with the Haar cascades because I think the data they use to train it is biased. So that's a whole other tangent. But so I'm going to take this example. I'm going to take Captain Picard, right? I'm going to do two things. I'm going to find skin tone blobs on him, and this is not perfect by any means. But like if you wanted to track hands and you had, say, something that was totally not skin tone, like green, like absolutely can do it. And I'll just draw those blobs. So right, so we're now making him into the green board alien being. But you also see that for some reason this red area down here in his shirt pulls up. Then we also, I'm going to try doing a different feature. So this time I'm going to try to find his mouth, right? So I'm going to use this mouth.xml Haar cascade, and that will basically return blob or return features that are the mouth. Then I'm going to load this image called stash, which I think you guys can guess what's going on here. So I'm loading this image called stash. I'm going to resize it to the width of the mouth that I find. And then I'm going to take the top left corner of the mouth, move it up ever so slightly in Y-space, right? And then blit this mustache image in at this new position and using a mask, using a binary mask, and show the results. So, here's the list of stuff that's actually inside of the Haar cascade. Right ear, left ear, face. And so you can do this automatically. You can totally do this in real time and sit there and have mustaches pasted on like everybody. Okay, so it's getting to be almost time to go. So I have one more kind of cool example that will motivate you into thinking about, like, okay, so we showed how, like, there's baked in stuff to find faces and stuff, but I wanted to talk a little bit about machine learning and, like, how you put this all together to build recognition of stuff. So basically, what we generally have tools for in Simple CV4 is what we call supervised learning. And it's basically where you show examples of stuff repeatedly, and then you can take those examples and you learn something from them, you figure out something about them, and you use them to find you test it on other data. I mean, there's unsupervised data or unsupervised machine learning where you say, oh, I don't know what I should use, and it figures it out for you. We're not that fancy yet. And so this is usually good for telling one thing from another, what we call binary classification. If you have cats and dogs, rats and bats, like if you have something where you say, it's either going to be this or this, it works really well for those cases. It works really well for, 3 or more cases where I have cats, dogs, and ponies and people. It works really well for those sorts of things. Or you can do like, is this the thing here? Is this thing not here? Those are generally the questions that you're going to be able to answer. The process is very general. You collect some data. You can either do this by manually scraping the web, or manually you can scrape the web. You can use existing data sets. Lots of research groups put their data sets out there. The way I work is I usually chop the data into 2 subsets, a training subset and a testing subset. I train on one and then test the results on another. The next step is that you take each of your images that are in your train and test set and you pull out a few numbers that kind of summarize what's in there. So in some cases, this might be numbers that are like related to the histogram of hues, or like the distribution of color in the image, or how vertical the lines are in the image and how horizontal the lines are in the image. What you then do is you take these values from each of the images and you put them into your classifier and you say, okay, here are the values I got for this particular thing. Here are the values for this particular thing of this class. You put them all in there and magic happens and out should come something that works or does not work. Once you finally get it to a point where you want to use it, you can then deploy it and see it in the real world. So there's a couple what I call feature extractors, which are these things that take images and distill them down into a few numbers that you can use for classification. So there's a hue histogram feature extractor, which returns, a histogram of hues, an edge histogram feature, which returns basically a histogram of edge angles, a Haar-like feature extractor, which is roughly measures of symmetry, would be the quick and dirty way to explain that, like shape and symmetry. Bag of features, which gives you little tiny gradient images, essentially, and morphology, which is basically your hue moments and a couple other things. We have a couple classifiers that are just baked in, really simple to use. There's the it's a KNN, which is just basically, here, take all this data. Here's all your examples. Now, if I give you something new, tell me which example it's closest to. It's the brain-dead classifier that you could, if you think about things really quickly, you would write. There's an SVM classifier, which is a support vector machine, which generally works on things that you can define a mathematical function that separates them. So if you have, say, apples and bananas, and you classify on color and shape, so you have, like, on one axis, the roundness of something, and on another axis, the color value from red to yellow, and there's a line that separates apples and bananas, it would find that line for you automatically. There's a naive Bayes classifier, which is roughly based on probabilities of things. So, the chance that you're going to get this versus the chance that you're going to get this and see this, it's roughly how you frame that. And then there's a tree classifier. If this thing is bigger than this, smaller than this, rounder than this color, it's probably this. So it kind of looks at logical things. A couple other tools in there. There's a Turking module, which is basically, hey, I scraped a bunch of images off the web, but some of them are total nonsense and I don't want them. That module will let you iterate through images really, really quickly and throw out ones you don't want. And there's also a confusion matrix class, which will help you figure out, like, what is being confused with what, and then you can kind of infer why. All right, so considering it's St. Patrick's Day weekend, and we're here, it's lunchtime, I'm thirsty, I want to look at how do you tell the difference between maybe images of beer, images of wine, and images of whiskey, right? And the reason is these actually fall into nice, good categories, right? Because if you look at images of wine, you have wine glasses that are either like this, or wine bottles that are like this, and they're either red or green, almost, red, green, or white, right? And then images of beer, you get beer steins, beer mugs, beer bottles, and they're different colors and different shapes regularly than wine bottles. And whiskey bottles are ever so slightly different, right? And they're usually in glass with rocks in it, so there's all these edges and color. So you can kind of say, these are the things I think this is going to look like, these are the things I think this is going to look like, and this other class is going to look like this. So I use that to motivate what I want to extract. So I screwed this up just a little bit. I'm going to create a hue histogram feature extractor. And I'm also going to create what is this one? An edge histogram feature extractor. Somehow this got deleted out of my notebook. So I create these two feature extractors, and sometimes they have parameters, sometimes they don't. I'm going to take this one out. Now, this may not work perfectly, but. So I created these two feature extractors. They're going to pull out information about color and information about the angle of the lines within images, right? And I'm going to go through a set of, or I'm going to create a support vector machine classifier and a tree classifier that uses these extractors, right? And then on these lines, I've already downloaded data using the image sets from Google Image Search and put them into different folders. So I have one for wine, one for beer, and one for whiskey. And the same is, I've divided these into two sets, a training set and a test set. And I basically define a list here of strings that I want to classify these things as. So one's wine, one's beer, one's whiskey. So basically what you do, right, is now that I've built these SVMs, or I've built these objects and separated out my data, I can just say, hey, SVM, learn whatever you're going to learn from this stuff, from these classes and from these image paths. Tree, learn whatever you're going to learn from these images using these paths and label them as this. And I can run everything and run my test data across it and see how well it performs. So take a second, but it's actually not that slow. I think I have 20 examples of each image. Okay, so these numbers, this first number here is the accuracy of the first classifier. And this number here is the second classifier. So you can see that like the first one, the SVM is 62% correct. It actually is higher when I add another classifier in there, or another feature extractor in there. And the one for the decision tree is actually 77%, which is, you know, not that bad. So it is detecting things. It's not 100%, but it is correct. So what I can do is I can actually create an image set and load in the data, the trained data again, and shuffle it and see how the classification performs. So I'm going to do that really quick here. Oops. And I probably should show this. And these are the results. So 77% is not that bad for 3 classes. I can actually make it more robust, and it would be more robust if I train it on more images. But you can see how you can kind of build up tools to help you figure stuff out. So these are the classes that actually come from the code using the classify method. Not, you know, I have no part in this. There's nothing up my sleeve, so it could be wrong. But it's generally doing all right at 80%. So this is just a crash course on machine learning, but I'd be glad to talk more about it. So we're close to done here, aren't we? So that's about all the results I have. So you guys should go have fun, use Simple CV, actually install it on your machines, and start asking us questions. All right?